So, welcome back to the second session on aerosol chemistry. It is my pleasure to introduce Professor Neeraj Rastogi. He is professor at the Physical Research Laboratory, Ahmedabad. Professor Rastogi is internationally recognized for his work on atmospheric aerosol chemistry, isotopic characterization of aerosols, brown carbon, oxidative potential of aerosols, and environmental microplastics. He currently serves as president of the Indian Aerosol Science and Technology Association, that is ISTA, and has made substantial contributions to understanding the sources, transformations, and impacts of atmospheric aerosols over India. It's our extreme pleasure to have you with us, sir, today for this session. I once again welcome you, sir, to this workshop. Over to you. Thank you.
So I'm starting now.
Yes, sir.
Okay. So very good afternoon to everyone present. I am Neeraj Rastogi and working at Physical Research Laboratory, Ahmedabad. And I would request any PhD aspirant, if you are looking for doing PhD, please go to the PRL website where we do research from means in a very large domain from interior of the earth to end of the universe. Multiple things are covered there. So you can go to the PRL website and see what kind of research we do. And if you are interested, you can come to do PhD here. Okay, and before I start, I wish to thank the organizer of this workshop, Aerosol Measurement and Retrieval Impacts, for giving me this opportunity to share whatever little bit I know about this topic. So as you can see the topic, why one should study the chemistry of atmospheric aerosols. So the way we will go, first we will talk about what are atmospheric aerosol, and then with time we'll go that why the chemistry of aerosol is important. So let us first start with aerosols. So you might have already heard, but in the order of completeness, let me also tell you again. Aerosols are liquid or solid particles suspended in the air. Now, if we talk about the major sources, the major sources can be natural, like sea salts. Sea salt means many of you, if you are living at the close to coastal region, if you go towards the sea, you see that sometimes you can feel the dust, uh, the salt on your body. So actually what happens that whenever this wave overturns, it traps the air. And when that air bursts, this sea spray, whatever salt dissolved in it, and that is how it is called sea salt or sea spray. Then you have windborne mineral dust. You might have seen there many places there is strong winds, dust comes in the atmosphere. Then we have volcanic eruption. It is not a continuous source. It happens once in a while, but whenever it is happening, it injects huge amount of aerosol in the atmosphere. Then you have biogenic sources like trees, pollen, spores, or dry tree leaf, plant debris, and all. They are coming in the atmosphere. They also release VOCs, which convert into aerosol, which we'll be talking about a little later. And then there can be forest fire. Again, this is not a continuous source because once in a while it happens, but whenever it is happening, it injects a huge amount of aerosol in the atmosphere. And then you have multiple man-made sources like industrial emission. Many of you would have seen the smoke coming from the industry. So depending upon what kind of industry is, it emits a variety of pollutants in the atmosphere. Then this is seen to everyone, vehicle emissions. Any city, anywhere you go, we have full of traffic everywhere, and you can see the pollution coming out of vehicles. That is vehicle emissions. This biomass burning, this is man-made biomass burning. And every year, this October, November, you hear this. There is a large paddy residue burning in Haryana, Punjab, and then thick smoke come all over the industrial plain and all. So that is biomass burning. And then we have a thermal power plant. So we need power, and for power, still major supply is through the thermal power plant, which uses coal. So there is a emission from thermal power plant. Then you also have this emission from cow dung cake burning, which is used as a fuel for cooking, which is reduced quite a bit now because of this Ujjwala Yojana and all. but still it is not removed completely. This is another source. So anyway, from whatever sources, things are coming in the atmosphere, and if they are solid or liquid particles, they are aerosols. Their size ranges from a few nanometer to several micrometer. We will be talking a little more in details about the size in next slide. Then these sources emit particles, primary particles, as well as precursor of secondary particles. What is primary particle? So if these or any of these source, if it is emitting solid or liquid particle, that is primary particle. But if these are emitting any gases and those gases are converting into solid or liquid particles, then it is called secondary particle. If we talk about the lifetime of aerosol in the atmosphere, especially in the lower troposphere, it is just about a week. In a week, by some mechanism, it comes out of the atmosphere. But it is not always a week, means it changes with the size and altitude. Very big size particle remove very fast, very small particle also remove fast, fine size remain for longer time. And altitude wise also, if somehow you can reach at stratosphere level, then aerosol can stay there for years. But within lower troposphere, we can talk about, it is just a week. Okay, now let us talk about the sizes. So before we go to especially in aerosol, let us see what we have in the atmosphere. Now see the scale. It is ranging from 10 to the power minus 10 to 10 to the power minus 1 meter. This is 9 orders of magnitude. What does that mean? We'll be talking in a minute. So actual size is from 100 picometer to 10 centimeter. This is what we are talking about. And this is all present in the atmosphere. In what form? Initially, if you have gases like sulfur dioxide, NOx, or ammonia, or VOCs, volatile organic compounds, these are the gases. Then these gases can form particle, as I was telling about the secondary particle in the previous slide. They can form particle like SOA, secondary organic aerosol, SIE, secondary inorganic aerosol. Then they can form particles, they can coagulate, they can coalesce, they can form cloud, fog, they can convert into rain or snow or droplets or hails and come back to the surface. So in a way, one molecule which was at this size may come back as 10 centimeter of big particle from the atmosphere. That is possibility in the atmosphere. Now, if you want to visualize, actually, when I say 9 orders of magnitude, what does that mean? So if we take 100 picometer as the lowest size, as an ant, a small ant, cheating, and then the biggest size we are talking about, it is moon. It is 3,500 kilometer. So in principle, an ant can become a moon in the atmosphere by different process. And many of them we will be discussing in the coming slides. Now, again, if you see, there is some kind of color coding. So if you see this all red, they are actually aerosols. Less than means lower side, this is gases, and higher side, this is rain, snow, droplets, or hails. And when I say then these particles from 1 nanometer to 100, 1 nanometer to 100 micrometer, this is the range of aerosol size. So again, this if you see as an analogy, it is coin of 3.5 centimeter, and this is 3.5 kilometer. This is a crater in Rajasthan, which is called Ramgarh crater. So a coin to a crater. This is the kind of aerosol size present in the atmosphere. Now, many of you would have heard word TSP. TSP is total suspended particulate, or SPM is suspended particulate matter. So if we are talking about all the size range from 1 nanometer to 100 micron, then it is called TSP or SPM. But if you are talking only about the particles which are smaller than 10, then you call it PM10. If you talk about particles smaller than 2.5 micron, then it is called PM2.5. If it is less than 1 micron, you call it PM1, and so on like that. It is PM.1, which is less than 100 nanometer or 0.1 micron in size. Remember, when we say PM10, PM2.5, PM1, and 0.1 are the subset of PM10. Same way for PM2.5, this and this are subset. For PM1, this is the subset. And TSP is everything together. So here, if you see carefully, size of aerosol provide a broad idea about their chemical composition. So for example, now if you are collecting aerosol just between 10 to 100 micron, then you are expected to collecting this kind of aerosols. If you are collecting just a particle less than 100 nanometer, so you are collecting these kind of particles. So you will be getting this kind of composition. If you are collecting PM10, then you can collect all these together, PM 2.5, then these together, and so on. So the question comes, okay, if these are aerosols are there in the atmosphere, let them be there. Why we are worrying about? So we are worrying because they affect us in a variety of ways, which you probably would have heard by the previous speaker. You will again hear from next speaker, but I'll be specifically talking about everything with the keeping aerosol chemistry perspective in mind. So we're talking about the role of chemistry in that. Okay. So when we say chemistry, so what are the major chemical species present in the atmosphere? So I'm talking about all the species, that means gas and aerosols. And I have put like this. So aerosols I have put like bold. You will understand why. So in the atmosphere, we can have variety of carbon containing compound with oxidation state varying from -4 to +4. For example, methane, NMSCs means non-methane hydrocarbons. BVOCs means biogenic volatile organic carbon. AVOC means anthropogenic volatile organic carbon. Then BC means black carbon. POA means primary organic aerosol. SOA means secondary organic aerosol. VRC means brown carbon. And then CO, CO2. Now you probably understand that this bold and this bold. So whatever things I have put in bold, they are aerosol and others are gaseous species. Then this, when we talk about these aerosols, especially POA, SOA, there can be thousands of organic species like any other component. In your high school and well, you would have heard this aliphatic compound, aromatic compound. Within aromatic, you would have heard polycyclic aromatic, that means PHS compound. Then dicarboxylic acid, ketone, aldehyde, ester, etc., etc. And all kind of aerosols are present in the atmosphere. Together, we are calling it primary organic or secondary organic. But if you go in speciation, there can be wide variety of compounds. Then you have nitrogen containing compounds with the oxidation states varying from -3 to +5. Examples, say ammonia, then nitrogen gas, then nitrous oxide gas, NO, HNO2, NO2, nitric acid, and then HNO3, nitrate and organic nitrogen. These are again aerosols, and the very low concentration of uh, nitrogen pentoxide and nitrate radical. Then you can have sulfur containing compounds with the oxidation state varying from -2 to +6. Examples, hydrogen sulfide, dimethyl sulfide, carbon disulfide, OCS, SO2, sulfate, and organic sulfur. So, as I told you earlier also, wherever we are talking, I am putting it bold means they are aerosols. Then you can have dimethyl disulfide or dimethyl sulfoxide and all. Then you have halogen containing compounds. So this is CFC means chlorofluorocarbons, SA means hydrochlorofluorocarbons, hydrofluorocarbons, halocarbons, etc. And they are all gases. As you see, I have not made them bold. Then you have ozone in the atmosphere. At stratosphere level, if you see, it is about 10 ppm concentration, which is about the total 90% of the total ozone present in the Earth system. At tropospheric level, it can vary from 20 to 80 ppb, which is about 10 to 15% of the total ozone. And probably you are aware that this ozone is like an umbrella for Earth, which is shielding us from harmful UV rays coming from the sun. Then you have mineral dust. We talked about the sources of aerosol and mineral dust. Now, in terms of chemical species, if we say mineral dust means it can have calcium, magnesium, sodium, potassium, iron, aluminum, manganese, silicon, etc. Then you can have sea salts. Again, you recall we were talking about the sea salt, but if we see in terms of composition, we know that the salt we eat also come from sea. So mostly it is sodium and chloride, but there is also sulfate, magnesium, calcium, potassium, etc. also within the sea salts. And then you have anthropogenic metals. So I was talking about industrial or regular emissions. So variety of combustions produce different anthropogenic metals in the atmosphere like lead, zinc, chromium, copper, cadmium, nickel, vanadium, etc., etc., etc. Now, overall, what we see that there are thousands of chemical species present in the atmosphere as aerosols. Obviously, they are not uniform in time and space. What does that mean? That means in the morning, whatever composition you have, in the afternoon, it will be different. In the evening, it will be different. Night, it will be different. If you go from place to place, that means Ahmedabad is different. Delhi it is different. Nagpur different. Chennai different. Bombay different. So at different places you go, the composition will be different. Why? Because the sources are different. Everywhere, all sources are not same. So depending upon the sources, this composition will also be different. And when all these things are different, so they also have different physical or chemical or optical characteristics. In addition to all these particles go transformation process during the aging. So I told you that their lifetime is just about a week, but within this week, they may transform. Now, if you recall, transform is ant can become moon. Recall that? So if ant is becoming moon, that means there is multiple transformations are going on within the atmosphere. So what kind of transformation are those? Let us just discuss a bit. So transformation process we talk about. So by now we know that we have aerosols in the atmosphere, and this aerosol can be organic or sea salt or metal or dust or black carbon or anything like that. Then you have some humidity in the atmosphere. RH is relative humidity. Depending upon the high hygroscopicity of aerosol, some RH will condense on this aerosol, and this will have now liquid water content. LWC means liquid water content. Now you have water also on aerosol. Then these gases, VOCs, volatile organic compounds, NOx, ammonia, and all these gases, they can diffuse. All these gases can oxidize by a variety of oxidants like hydroxyl radical or hydrogen peroxide or ozone or nitride radical. Different oxidants are active during different times. So nighttime, nitride radical is more active, daytime, OH radical is more active, but different by different oxidants. Now these gases get oxidized and form sulfate or nitrate or sulfate or brown carbon at the surface of existing aerosol. So now, as I was talking about the transformation process changing, and the if you again recall, this is these are the processes which are making ant into moon. So because of this, there is a change in characteristics like physical, chemical, optical, and isotopic characteristics. What does that mean? So there is a change in size. So you have some small size. Now you are coating on the surface, you are increasing the size. You change the surface properties, like for example, black carbon or dust, they are hydrophobic in nature. That means they don't like water. But if you have a coating of sulfate or nitrate at the surface, they become hydrophilic. So suddenly they start liking water. Optical properties. Earlier, black carbon is absorbing type, but if you have a coating of sulfate, this optical property will be different. Change in the bioavailability of nutrients. So when we say bioavailability, what does that mean? Say if you have some 100 gram of iron which you are putting in the ocean, but all 100 gram is not useful for the phytoplankton present in the ocean. Only soluble fraction is important for them. So if 1% is soluble, so out of 100, only 1 gram is going to them. But because of this process, if you decrease the aerosol pH, increase the solubility, so down from 100, instead of 1 gram, it may go 5 gram, 10 gram. That means 5 times or 10 times more soluble iron is going. And then that is how it can affect the surface ocean biogeochemistry, which I'll be talking a little later in the presentation. So overall, what we see that we all have different sources, different transformation processes, and they can affect, they can change physical, chemical, and optical properties. Then aerosol, as I was telling that lifetime is just about a week, they get removed from the atmosphere. How do they get removed? They get removed by dry deposition, which happens around the year, and these processes include sedimentation, like simple undergravity, diffusion from higher concentration to lower concentration, impaction. So while flowing, if it hits any surface, it gets attached there, or absorption. So many of you would have seen at home is your home is say at 10th floor, 12th floor of a building, but still you see dust on different objects in your house. They are all aerosols, and for during following this process, they are getting deposited on those surfaces. In addition to dry deposition, there is a wet deposition, which is the major removal pathway, which is active during rain. So when rain is happening, whatever is present below the clouds, they all get removed from the atmosphere because of the means rain get dissolve them and brought back to the surface. But if how something has been crossed over the clouds, that means it has reached to stratosphere. So then it is not coming down, and that is why lifetime in stratosphere is order of years. But if it is within lower troposphere, that means below clouds, it is about a week. Okay, moving further. So again, the question comes, so these aerosols are there, let them be there. If they are getting deposited in my home, I will dust it, I will clean it with the cloth. What is the big deal? Why should we worry about that? So what are the effects of atmospheric aerosols? So they affect in a wide variety of ways. So they affect our climate. How? So they affect radiation budget. What does that mean? That energy from the sun is coming in short wave radiation. From the earth, it is coming out in long wave and short wave both. And if they are balanced, everything is fine. But somehow, if you increase the incoming or decrease the outgoing, then it will warm. Same way, if you reduce the incoming and increase the outgoing, then it will cool the earth. So depending upon what is there in the atmosphere, it can affect the energy balance or and then it can warm or cool the earth. Then aerosol also affect hydrological cycle. How? Aerosol as a seed for cloud. There in the atmosphere, we have water vapor also in the atmosphere, but water vapor is not able to condense. But once they have aerosol, which are providing the surface, they condense at the surface of the aerosol and form cloud droplet. That cloud droplet may become rain and come back in the form of precipitation. But as I said, RH is getting attracted to the particles. But if the particle is hydrophobic, I was talking about black carbon and dust, then it will not allow water to come and sit on it. But if it is hydrophilic, like sulfate aerosol, nitrate aerosol, or water soluble organic aerosol, they love water. They will welcome water vapor to condense on. So depending upon what kind of aerosols we have, they can affect the precipitation, which we will talk till more in details in coming slides. So it can affect radiation budget and hydrological cycle, and that is how it is affecting our climate. Then it affect our air quality. If you are living in a big city and go at the terrace and see around, you see this kind of dirty atmosphere in the surrounding. These are all haze because of aerosols. This is a picture from satellite. If you, some of you can recognize, these are Himalayas, and this is Indo-Gangetic Plain, and this is Bay of Bengal. And this thick layer is because of aerosols. So aerosols are such high in concentration, you can see them from the satellite. So yeah, they are affecting air quality. Then they affect human health. How they affect, we will talking in details in the coming slides. And then they affect atmospheric chemistry. So the way, as I was telling you, that they welcome RH at surface, same way they provide the surface for different gaseous species and allow them to come at the surface and react and do the different kind of reactions. Many of you, if you are from chemistry background, you know that in order to make any reaction happen, you have to have molecules together. They should interact and then only their product can form. And for that, aerosols provide the surface. And that is how it affects the atmospheric chemistry. And it also directly participates in the atmospheric chemistry, not only surfaces providing surface, but directly also it can affect the atmospheric chemistry. And then it affects our aquatic ecosystem. So now, if you recall, I was telling about the removal of aerosol via dry and wet deposition. So if those aerosols are getting deposited over ocean, so that is actually become the supply of nutrient to the remote ocean or lakes. So aerosols having all kind of nutrients like nitrogen, phosphorus, iron, etc., etc., and they are putting the nutrients to the ocean or remote lakes via atmosphere, and that is how they affect the aquatic ecosystem. Again, this will be I will be talking a little more in details in the coming slides. And then it can also cause acid rain, depending upon again what kind of composition we have. If you have too much of sulfuric acid, nitric acid kind of compound, it may result in the acid rain. In India, we don't see too much acid rain because our soil is quite calcareous. So it is you have too much calcium, magnesium, sodium carbonate, which can easily neutralize the acid. So that is why you don't get acid rain. But if you go to temperate regions, there are multiple places where acid rains are recorded, and they can affect in wide variety of ways, including from monuments to crops and all kind of things. And in any effect we talk about, the size and composition are the important factor. So for example, if somebody had talked to you about the optical properties, and then he or she would have talked to you about the size parameter. So depending upon the size, scattering efficiency will be different. So if the aerosol size is similar to the wavelength of the sunlight, for example, in the middle, that is green wavelength, so then this scattering will be maximum. Otherwise, it will be different. And composition, as I was telling you, if it is hydrophilic, it is different way it behaves. If it is hydrophilic, it behaves differently. Same way, it can absorb or scatter, so it behave differently. So size and composition both are important in assessing the effects. And then again, if you recall, I was talking about the transformation process, which again can affect the size and composition. So initially size or composition was different, but after transformation, the size and composition became different. So all these things are important when we are trying to study of the effects of aerosol on our Earth system, whether it is climate or air quality or aquatic ecosystem. Then the question comes, so okay, aerosols are there in the atmosphere, but how do we measure them? What are the ways by which we can measure? So there are multiple ways, offline, online. I will tell you what does that mean. And this range from ground-based sensor, that means you can do the measurement at the ground level, at surface level, all the way to the polar and geostationary satellite. From satellite also you can make measurement. So we'll be talking a little more in details now. So first let us talk about the offline sampling. Offline sampling means you take a sampler. This is called high volume sampler, which has a flow rate of 1200 liter per minute. And this is the filter before you blank filter without aerosol, and this is with aerosol. That means after some 12 to 15 or 24 hours of sampling, this kind of aerosol you are collecting on this kind of filter. Then you have LVS, low volume sampler, which has a flow rate of 17 lpm, liter per minute. So LVS is about 70 liter per minute, HVS is 1200 liter per minute. So we are using smaller filter here. Again, this you can see this white portion is the blank filter, and these are collected aerosol in different environments. So you can see different colors. In addition to this, they both are filtering the aerosol through the filter. This is how you're collecting. You have impactor, which is not by filtration, but it is by impaction. So here you pull the aerosol with a certain flow rate. So bigger particle hit first, smaller particle will pass through and hit second plate. Further smaller particle can again pass through and hit the other plate, and that is how you get the aerosol on different plates. And this is how they look like. So this is bigger particle, then smaller, then further smaller and further smaller particles. And usually the cascade impactor has a flow rate of 30 liter per minute. Now, how do you decide the sampling? Samples are all, when we're talking about the outdoor air, so they are collected outdoor, that usually at the terrace of a building or any sites above the ground level with a free flow from all the sites. Duration of sampling depend upon where you are doing the sampling, whether it is polluted or pristine site. For example, if you are doing sampling in polluted city like Delhi, then you can collect few hour sample and you will have sufficient sample like this. But if you are at a place like Antarctica or Arctic or Mount Everest or any very clean place, then few hours will not be sufficient to collect sufficient aerosol. Then you have to run for 2 3 days or even more number of days to have sufficient amount at the filter so that you can bring it back and do the analysis in the lab. And what kind of analysis we do? There can be wide variety of things like water solvent inorganic species. That includes sulfate, nitrate, ammonium, sodium, calcium, magnesium, etc., all ions. Then you can measure trace metals like iron, aluminum, lead, zinc, etc., etc. You can have water soluble organic OC means organic carbon, and water soluble TN means total nitrogen. You can have bulk organic and elemental carbon, which is called OC and EC. You can have organic speciation. When we say speciation, it means now you are trying to find out whether it is pHs or aliphatic or alcohol or ketone or ester or what. So then it is organic speciation. Then you can have brown carbon. This is a type of organic carbon which are absorbing in nature. Then you can do the speciation of brown carbon. You can measure oxidative potential. Little bit we will talking about in the coming slides. You can measure variety of stable or radioisotopes. They are for very specific purposes, which I will not be discussing today, maybe sometime later. And then very new things people can collecting aerosol for several hours or several days. Here you are not collecting for several hours or several days. It is every minute. Every minute you are getting data. So you have instrument like environmental beta attenuation monitor, which is called EBAM for PM mass concentration. And now these are very popular thing, low cost sensor, again for mass concentration. Now if we, in addition to mass, if you're also interested in getting the size of the particle, then we use scanning probability particle sizer, which is called SMPS. Then if you want to do chemical speciation, there are instruments like aerosol mass spectrometer, which measure non-refractory organic and inorganic species. Non-refractory means up to certain temperature, means say up to 600 centigrade, whatever can volatilize, it can measure that. If you have volatilization after that, that means dust particle and all, it cannot measure. But other compound, this EMS can measure. And then you have this X ambient continuous metal monitor, which is called ZAC, and this for metals in the atmosphere. You have athlometer for black carbon measurement, and these are all at down level. And this, if we talk about, this is from satellite, remote sensing, and you have very multiple passive or active remote sensing sensors at the satellite, which are doing the measurement for aerosols. So in short, as a summary, if we see, so when we talk about aerosol measurements via multiple ways, offline or online, so you can have in situ or ground-based measurements like filtering through filtration, high volume, low volume samplers, through impactor, cascade impactor, and then do gravimetric analysis and do variety of ions and metals and carbon, etc., in these filters. You can have online measurement by SMPS. APS is aerodynamic particle sizer for particle size distribution. OPC is optical particle counter, particle number in percentage for particle number in size concentration. Nephelometer for scattering coefficient. Athlometer for black carbon, AMS for real-time chemical speciation of non-refractory mass, radar for aerosol backscatter and vertical profiles. And you can do the measurement at surface layer, in boundary layer, you can use drone or balloon, and you can do vertically and from satellite. As I said, variety of measurements are already available. So you can have polar satellites or you can geostatic satellites. Variety of satellites are listed here. This is our own satellite INSAT 3D. So overall, these are the instruments and these are the application. So for aerosol measurements. Now let us move further. So now we talked about aerosols, what are aerosols, size, composition, what kind of species, etc. Now the question comes, why one should study the chemistry of atmospheric aerosol, which was the topic of my talk. Now the answer is to identify sources and processes affecting aerosol abundances, and also to understand and assess their effects ranging from air quality to climate change and planning the mitigation strategies. I will tell you a few examples in detail. I have few things which I am not going to tell, let me tell here only. So to identify sources, for example, if you are not doing chemistry, if you are just doing physical or optical properties, you will say, okay, this some particle is there of this size. But what is that? You don't know. But if you are measuring the chemical composition, you can say, no, no, it is sea salt. No, no, it is ammonium sulfate, or it is dust, or it is metal, or black carbon. So once you identify the particle chemically, then you can say, then you can think of the sources. If it is sea salt, that means it is coming from sea spray. If it is dust, you can say it is coming from windblown dust. If it is some kind of metals, which is from certain industries, you can say that industry has emitted the particles which you are getting. So in any kind of medications, if you are planning, you should know the sources. So that is why it is important. Processes, again, if you regard transformation processes, which affect many things about aerosol, which help aerosol or which help ant to become known in the atmosphere. So you should understand the process. And then another effect, which I'll be telling you more in details now. So now let's talk about how composition, aerosol chemical composition and earth radiation methods are connected. Just a second. So now if you notice, I am telling little more in detail whatever I showed you earlier. We have sun, we have earth, radiation coming in, going out. Things are balanced, everything is fine. But now you have aerosol in the atmosphere. What they can do, they can reflect the incoming radiation, and reflecting type of aerosols are sulfate, nitrate, and organics. They can absorb and irradiate. What kind of aerosols are they? Black carbon, brown carbon, dust kind of aerosols. They can form clouds and then reflect, which is this is direct effect. This is indirect effect. We know that they act as a cloud condensation nuclei. Hydrophilic species are more effective than hydrophobic species. We have oppositely. I gave you the example earlier. So this process affect the cloud lifetime, precipitation, and different type of aerosol have different effect on earth relative forcing, mostly negative. Negative forcing means it is cooling the earth, but overall means aerosol cools earth. That's correct, but they have many other adverse effects. Now aerosols and rain, if we talk about, so again this is indirect effect, which we discussed in earlier slides. Now, see, this is clean cloud, this is polluted cloud. What does that mean? So you have some amount of water vapor available in both the cases. And you are putting number of, if you again recall, I told you that aerosols are seeds for cloud. Now, but if you are putting too many seeds, so what will happen? That the amount of water will be distributed over more number of seeds. Then the rain droplet which you are forming will become smaller. So more number of smaller cloud droplets are formed, less number of ice crystals are formed. That will cause the less precipitation. You will have cloud in that atmosphere, but it will not precipitate, and there will be more absorption. This will increase the cloud albedo. Cloud albedo means reflectivity. If you have more cloud for longer time, they will reflect more. It also increases the lifetime of the cloud. It will not precipitate. It will just remain in the atmosphere. And there will be increased evaporation. If you have absorption, the cloud droplets can evaporate. Unlike if you have a clean cloud, less number of seeds, you are making more number of bigger size cloud droplet and ice crystal, which reduce cloud albedo. There will be more precipitation and less cloud time. So overall, this is the process which has shown that how this cloud macrophysical process behave. So we have different water vapor molecule condensing on aerosol, and then they coalesce together from rain droplets. Again, they coalesce together for the bigger rain droplet, and it fall that at the ground. Now the question comes: how aerosol affect our health? This is very important part. Everybody is concerned. We are all concerned. And for many years, it is understood that aerosols affect our cardiovascular system, which includes coronary artery diseases, heart attacks, strokes, blood clots. It also affects our respiratory system. It includes chronic obstructive pulmonary diseases, asthma, lung cancer kind of diseases. This is known for a longer time, for multiple decades. But there are growing evidences that the effect of air pollution are much beyond the respiratory diseases only. What are those effects? The aerosol can affect our brain. It can cause Alzheimer disease and cognitive decline. You probably know Alzheimer means you are forgetting everything. You don't remember anything. Cognitive decline means your reasoning power is decreasing. It can affect your nervous system, which called Parkinson disease. You might have seen some people have this shaking hand. It's a part of Parkinson disease. You can have other neurodevelopmental disorders. They can affect renal system and they can cause chronic kidney diseases. They can affect endocrine system, called obesity. It can cause obesity or diabetes. It may affect reproductive system, which can diminish the fertility. It can cause premature births. It can cause low birth weight. Even people have seen that aerosol particle affect embryo. Soot particles, which are actually black carbon, are shown to reach the lungs and brains of infants even before they are born. So now you see how deep aerosol can reach and what kind of effect they are causing on us. Some are known, many are unknown. And these effects can be acute or chronic. What is the reference? Acute means immediate effect. Suppose means, there is a huge pollution and some people are dying. So that is called acute effect. But chronic effect is like a slow poison, and which we are facing every day. You are passing by the huge traffic, you are inhaling the all kind of pollutants, which is not affecting you immediately, but slowly they are affecting your health. I will tell little more detail about this. So okay, let us discuss that. So how deep this aerosol can reach in human body? Now, if you recall, I told you that aerosol has a wide variety of size. You remember coin to crater. So this small are coin and this bigger are crater kind of. But your nose was designed by the Almighty in such a way that all the particles bigger than 10 micron in size, they can't cross nose. They are trapped in the nose itself. Now you understand that why the PM10 means you can have PM8 or PM12 or 15, etc., etc. Not. We said PM10. So this was the reason why we are talking about PM10. PM10 can reach from this region, trachea region. Then if you have further smaller particles, which is PM2.5, again recall, I told you about what is PM2.5. Then they can go deeper in lungs, up to here. Further small particle, PM1, again recall PM1, they can reach deep inside the lungs, which is called alveoli region here. And then again, if you recall PM zero point 0.1, that is PM less than 100 nanometer, ultrafine particles. They have a capability to pass through the macrophage and get into the bloodstream. And we all understand that if something is reaching to our blood, that means it can reach to any part of our body. And if it can reach any part of our body, it can affect the way as we discussed in the previous slide. But this is also true that particles go in with the inhalation and comes out also with when we exhale. But a fraction of particle get deposited to the epithelial cell. What are epithelial cells? If you can see inside our lungs, so whatever cells you see in the surrounding, they are called epithelial cells. So how do they affect actually? There are multiple mechanisms, and one of the mechanisms which are quite accepted is through ROS imbalance. What is that? ROS means reactive oxygen species. You know, in our body, we have antioxidants like glutathione or ascorbic acid. We have oxidants also in our body like hydroxyl radical, superoxide ion, hydrogen peroxide. So if there is anything or imbalance favoring oxidants or disfavoring antioxidants, that leads to damage of variety of damages, ROS imbalance, which causes oxidative stress, inflammation, and cell death, and which results in variety of diseases, which we were discussing in the previous slide. And again, if you recall this word oxidative potential, so capacity of particles or aerosol to generate ROS and or deplete antioxidant is called the oxidative potential. So within aerosol, if they have high oxidative potential, they will cause more ROS imbalance. If it has less oxidative potential, they will cause less ROS imbalance. Usually, the natural aerosols are having less oxidative potential, whereas anthropogenic aerosol they are having much more oxidative potential. That means anthropogenic aerosols are very toxic compared to natural aerosols. Okay, then I was talking to you in the beginning, if you know, recall the nutrient supply. So we have already discussed, we have a variety of sources from different processes. These aerosols, through atmospheric transport, these aerosols are going from continent to remote regions. Again, you recall, they get removed over the land or ocean via wet or dry deposition. They get removed from the atmosphere. It can be rain, cloud, fog, or under gravity or turbulence settling. Again, if you recall, atmospheric processing or transformations can change the bioavailability of nutrients. I gave you one example. Now, suppose this is the dust, and this dust contains 100 gram of iron. That whole iron is not bioavailable. Only a small fraction. But bioavailable is whatever soluble fraction is there, that is bioavailable. But because of this transformation process, this bioavailable fraction can increase and then it can affect in a variety of ways. So what are the nutrients it can have? It can have macronutrients like nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, etc., which are essential for plant productions. These nutrients and trace elements are delivered by aerosols. They can be trace metals like iron, manganese, zinc, copper, cobalt, nickel. They are required for cofactors for enzymatic and metabolic processes. You can have micronutrients like silicon, molybdenum, boron, vanadium. which supports specific biological functions. We can have variety of organic matter, which can be dissolved or particulate organic matter, like amino acids and lipids. They all affect means act as nutrient. And their effects, if we talk about, they enhance the primary productivity. Primary productivity means these are the kind of food available for fishes. If you increase, that means you can increase the number of fishes. And if you are changing, and this also affect the carbon cycle. I will tell it in detail. So it can enhance the primary production by this kind of nutrients. It can alter the community structure, the shift in phytoplankton species composition and diversity. There can be changes in the nutrient cycle like nitrogen, phosphorus, silicon, and trace metal cycling in the surface ocean, which can increase regeneration or increase demineralization, influence the carbon cycle. So during the process of phytoplankton, it needs carbon dioxide, which it takes from the atmosphere. So in a way, phytoplankton formation process is removing that CO2 from the atmosphere, which is, you may be knowing that ocean is a major sink for carbon dioxide from the atmosphere. When it is removed in the some form, it can go down to the deep ocean, and that is removed for many long time, millions of years. Again, depending upon what kind of aerosols you have, it can affect the surface pH and ocean acidification, deposition of nitrogen and sulfur compounds, can modify pH, and that can affect the buffering capacity. All these processes can affect the ecosystem and fishery impacts, changes in food web dynamics and productivity, and ecosystem balance. So overall, if we talk about aerosol linked distant continents with remote aquatic ecosystem influence global biological cycle and climate. So atmospheric aerosols are a vital natural pathway for delivering essential nutrient and trace element to the remote ocean and lakes, which profoundly shape surface biodiversity and ecosystem health. Now, if I summarize everything together, so what does that mean? Aerosol affect our environment in many ways, from air quality and human health to climate change and aquatic biodiversity. We have seen the example of almost all of them. Aerosol aging, which is transformation, is the in the atmosphere causes numerous transformation in the physical, chemical, and optical properties, which in turn can modify the assessment of aerosol effects. I told you when we were talking about the transformation process. Then, in any effect we are talking about, studying chemistry of atmospheric aerosol is inevitable to understand any effect of aerosol. But overall, only chemistry also will not help. So overall, when we say comprehensive studies on aerosol physical, chemical, and optical characteristics with a good temporal and spatial resolutions are important to effectively understand the impacts of ambient aerosols on our environment and plan appropriate mitigation strategies. With this, I wish to thank you all. And if you have any questions, I'll be very happy to answer.
Thank you, Professor Rastogi.
Yeah.
It was a very enlightening session, and we have several questions. Shall I take them
Yeah,
for you?
please.
So, one Ragvi Vashne is asking, how has aerosol chemistry changed due to increasing industrialization and urbanization?
Okay. Good question. So when we say industrialization, depending upon what kind of things you are producing in that industry, you are injecting those chemical species in the atmosphere. And those chemical species can be anything, and their effect on us can be wide variety of things. And urbanization means actually you are talking about the increase in population, and increase in population means you will increase the vehicular emissions, you will industry also will increase. Once you increase the population, almost all anthropogenic sources are going to increase. And we discussed the effect of anthropogenic aerosols. Yeah.
Yeah. So Anushka is asking, please explain the process of secondary organic aerosol formation.
Again, I have not gone in the greater detail of secondary organic. If you recall, I was talking about VOC and AVOC. VVOC biogenic volatile organic carbon. AVOC means anthropogenic volatile organic carbon. So these are volatile gases, but once they are coming in the atmosphere, they get oxidized, and they more and more oxygen you are adding to it. in a way you are increasing their molecular weight. So they then fractionate from gaseous phase to particulate phase. So in a way, you are changing from gas to particle. If you again recall when I was showing the size range from 100 picometer to 10 centimeter, that I was talking about different gases are converting into the aerosols. That includes secondary organic aerosols also.
Mhm.
Yeah.
Another question is, does the toxicity of black carbon cause higher cardiovascular risk than natural mineral dust?
Okay. So let me tell you, black carbon itself is not toxic. Black carbon is kind of inert in nature, but it has a porosity. That means it itself is not dangerous, but it can hold variety of toxic compound means species within those pores, and then it is transporting. And the size is very fine, so it can reach very deep. Again, if you recall, when I was talking about the size of aerosol and less than 100 nanometer, that means it can go to your bloodstream. That means any part of your body. So that means black carbon can carry some toxic metals like lead or nickel to any part of your body, and then it can affect.
Yeah.
Yeah.
We can take a couple of questions more. One is, what are the primary chemical components found in Indian aerosols during winter versus summer?
Okay. So usually, whenever we talk about aerosols, they don't have any nationality. They are everywhere, anywhere. So it is not the thing called Indian or Bangladeshi or Pakistani or US or European aerosol. Aerosol means if those kind of sources are there, those kind of aerosols will be there. In India, as you know, that we have wide variety of sources for, and those sources are changing. Again, if you recall, I was talking about time and space, things are very different. Say, for example, October, November is coming. Again, that if biomass burning is happening, you will get too much of particles. Now you can call it Indian aerosol if it is within India. But anywhere, say it is forest fire, which is happening any place, that also it will inject. So that depends upon what kind of process. So aerosols are more on the source and process dependent. Yeah.
Uh, So one last question, sir. How do high aerosol loading suppress warm rain formation in shallow clouds?
Okay. I didn't discuss that, but okay, since you asked. So how do high aerosol loading reduces warm? Can you repeat the question once again?
Yeah, how do high aerosol loading suppress warm rain formation in shallow clouds?
Okay.
I think it wants to
Okay.
suppress rain formation in the shallow clouds.
Yeah. So now again, if you recall, means I was telling when I was talking about the aerosol and cloud, then I told you that given amount of water vapor, if you put too many seeds, so per seed water vapor will reduce. That means you are not allowing water vapor to grow to become rain droplet and fall down. If you have lower concentration, then you will have bigger droplet and it will fall fast. So clean clouds and polluted clouds, one slide I have shown. So it can be understand from that perspective. But here, not only loading, but what kind of loading. Means aerosol composition is also important. If you are loading too much of ammonium sulfate of kind of aerosol, which are hygroscopic, they may have different effect. If you are injecting too much of dust or black carbon, they may have different effect.
So with this, we thank Professor Rastogi for delivering such a wonderful talk. It has inculcated lots of curiosity among the participants. And if there are further questions, sir, I may be posting to you. If you find time, you can
Fine.
please
So in the last
reply.
slide, I showed my email ID. You are welcome to contact me anytime. All the participants. Thank you.
Thank you
Thank you
so
very
much,
much.
sir. Once again, thank you. Thanks a lot from IIRS. Thank you, sir.
Thank you. Thank you.
Yeah, so welcome back. Our next speaker is with us. He is Professor Sadnik Dey, Institute Chair Professor at the Center for Atmospheric Sciences, IIT Delhi, and Coordinator of the Center of Excellence for Research on Clean Air. Professor Dey is one of India's leading experts on the air quality climate health nexus. His research has significantly influenced understanding of air pollution exposure, health impacts, and evidence-based air quality management strategies. His work has been widely published and has contributed directly to the policy discussions on clean air in India. Sir, we are glad to have you here with us. Over to you, sir.
Okay, thank you for the kind introduction. Hope I am audible.
Yes, sir, very much.
Yeah. So it's great to talk about the work that we have been doing for the last 1.5 decade or so. And I must acknowledge the contribution of my students and all collaborators within India and outside India. Because as you will see that, when we talk about air pollution and its impact on health, it's a completely interdisciplinary uh, approach. So before I talk about some of the results, I want to mention first that there are a lot of misconceptions when it comes to air pollution and its impact on health. You, when you think about air pollution, of course, it comes to the mind that there is some negative impact on health, and this is why actually we are concerned about poor air quality. However, the misconception is how the health impacts are quantified. When we say that this is the impact, how it is actually, quantified? How do we arrive at the numbers that are projected out there? So I will try to give you a very brief overview. Now, let me tell you that the methodologies to do that have evolved over the last 40 years. However, in India or in general in South Asia, there are not much training or knowledge about how you do air pollution epidemiology. And this is where I think, in India, in terms of the capacity building, we are lacking. We have trainings, we have students, who are working in climate modeling and many other things. But when it comes to connecting environmental aspects with the health, a separate skill is required. Now, one important point to keep in mind again is that air pollution is a risk factor. What is the difference between a risk factor and an outcome is that air pollution does not directly kill a people. You can draw parallel between air pollution and smoking. Smoking also does not kill a person. Smoking causes multiple health outcomes like cancer, high blood pressure, and people die because of those diseases. So first we need to really understand the difference between risk factor and diseases. Risk factors cause diseases, and those diseases actually cause impacts, eventually, killing a person. The task is challenging because for same disease like high blood pressure, for example, you can have different risk factors. Your air pollution can also cause high blood pressure. Smoking can also cause high blood pressure. Diet, lifestyle, stress, all of these risk factors can also cause high blood pressure. As I said, over the last 30 to 40 years, methodologies have evolved how to really attribute that particular outcome. In this case, we are discussing high blood pressure to different risk factors. And now we have fairly good idea how to do that. For example, if we know that 100 people in any geography have died because of high blood pressure or stroke or something else, out of those 100, how much you apportion to smoking, how much of you apportion to lifestyle, how much of you apportion to stress. So what you are essentially saying in mathematical format is that any health outcome is a function of many risk factors, which are x1, x2, x3, x4, like that. And statistically, if you have data at a population scale, at an individual level, you can quantify the relative proportions. That means how much is the effect of x1, which is a risk factor, how much is the effect of x2, which is another risk factor. And the beta, if you see this regression equation, typically betas are the coefficients that determine which of the independent variables that influence that particular health outcome can actually be given more weightage or not. Higher is the value of beta, higher is the weightage of that particular risk factor. Now there are four important things when we sort of try to assign or attribute risk. One is, of course, first you need to know how do we assess exposure to any risk factor. And as I said that because there is not a single risk factor for any of the disease that you can think of, you have to adjust the effect of all other risk factors, which we call as the confounder. So when I'm saying that this is the effect of air pollution, I must adjust, in fact, the effects coming from all other covariates. When I'm saying that this is the risk for smoking, I have to adjust for all other covariates. Same for every risk factor. Effect modification is very, very important because even after adjusting for the confounders, what we found is that depending on socio-demographic information and many other factors, the effect may not be similar. And I will give some example later on. And finally, of course, you have to interpret the results in the context of study design. Now, in epidemiology, there are many study design. The best one, of course, is the randomized control trial. And then the next best is the cohorts, where you individually follow up subjects or people, do the measurement simultaneously, both for the exposure and the health outcome. And because you are individually following up for every person, you can then do the effect modification as well as you can adjust for confounders and come up with causal pathway. However, it is not possible always to do those kind of studies because they are super costly. Just to give you an example, I am part of a cohort, which is a mother-child cohort, and I'll show again one example later on, where the cohort is being run by this DBT institute called THSTI. They are recruiting pregnant mothers, following up the mothers. And so far, in the last 7.5 years, more than 12,000 pregnant mothers are recruited in the study. And we are, of course, doing the exposure, environmental exposure, and sort of this, things like that. But the cost of running such kind of cohort is almost 25 to 30 crore. Just a cohort of 12,000 subjects, because individually you are following up a patient, you are taking their measurements, biological samples, and all of these things. So it's a quite resource intensive effort. So the next best thing is doing cross-sectional analysis. And I will again show you some examples and how we are generating evidence when in India, due to lack of resources, we do not have many such cohorts. We rely on secondary health data that is collated by the health ministry and come up with risk attributions. But the first step in all of this is exposure, which comes under environment, environmental science, but exposure attribution is also not that easy. If you think about exposure and in the context of air pollution, the best way to measure a person's exposure to any of the pollutant is if the person carries an instrument which measures air pollution level. So if I carry an instrument which measures air quality, I carry 24/7, that's the best estimate of my exposure to that particular pollutant. And we'll take an example of PM 2.5, which is the most important pollutant, as you know. It's the fine particulate matter smaller than 2.5 micron aerodynamic diameter. Why it is important? Because when we breathe in, these fine particles go into our body and then it basically enters our bloodstream. But if you think logically, carrying a sensor 24/7, 365 days is not feasible. Nobody will agree to carry the sensor. So, what is the next alternative? If we have to assign exposure at a population scale, the next best thing is that if I take a ground monitor, these are the air quality stations maintained by Central Pollution Control Board. And we can assume that people living nearby that ground monitor, they are breathing typically the pollution level what is reported by that particular monitor. So far so good. But if you see the India statistics, only 2% of Indian population lives within a 2-kilometer radius of a ground monitor. So it means that 98% people, they live more than 2 kilometers away. And if you do actual measurements on ground, you will see that air quality changes if you go far, away from a monitor, because the spatial heterogeneity is too much. So how do we really do our job in assigning exposure to the population? And this is why actually alternate methodology has evolved. We need information about air pollutants at a high spatial and temporal scale. The best alternative so far is using satellite derived information. Our group has specialized in generating air quality information using satellite data, and we have standardized the algorithms for India. We are doing a project with, for Central Pollution Control Board, where we generated PM 2.5 surface concentrations for the country at a daily scale at 1 kilometer by 1 kilometer spatial resolution. And I will demonstrate how we are doing it. So you know that satellites, they do not measure surface PM 2.5 or any surface air quality information. So what they measure is a columnar quantity called aerosol optical depth, which is the columnar attenuation of solar radiation. Now, we have standardized the conversion of this columnar quantity, which is aerosol optical depth, to surface PM 2.5. How did we standardize? So, on any given day, if you see, for example, 1st November, sorry, this is 1st January 2021, this is the map of satellite derived aerosol optical depth. You have a lot of gaps because 1st January has cloud and sensors cannot retrieve aerosols if cloud is present or fog is present. So that you have in any given day a lot of data gaps. So first what we have done is we have filled this data gap using machine learning. And I'm not going into too much details about the methodology. You can read the published articles. So we train machine learning models based on predictor variables, fill the data gap. And then we converted the columnar aerosol optical depth into surface PM 2.5, which you can see now, again using a hybrid approach. Now, if you see the spatial pattern of aerosol optical depth and the spatial pattern of PM 2.5, they are not matching. And of course, they will not match because the ratio of PM 2.5 at the surface and the columnar aerosol optical depth depends not only on meteorology, but also it depends on the vertical distributions. So when you are sort of predicting that, you compare with existing ground measurements on a daily scale for more than, you can see 75,000 data points. We have achieved an R square of 0.86. And keep in mind that, we are the only group that are developing daily PM 2.5 using satellite. There are many global efforts where monthly PM 2.5 is developed. And from Delhi, in fact, now we have already developed an hourly product in our more recent, work with the Central Pollution Control Board. But here I'm just showing the results of Delhi. And you can see the daily, monthly, and annual scale. Of course, as you move from daily to annual time scale, the uncertainty, of course, is much lower. But if you have this kind of data set, you can use them in now health studies. But before talking about health studies, I'm showing you that typically you have a large spatial and temporal gradient in PM 2.5. Since we have developed the data for the last 25 years, we looked into, climatologically what happens when you move from 1st January to 31st December. So this is what I have done is that I have taken all the last first 25 1st January, average them, and this is your results. And if you see on 1st January, you have very high pollution in the entire Indo-Gangetic plain. Although I have masked outside India, but typically the pollution spreads from Pakistan to Bangladesh, cutting across the entire North India. And the reason is very well understood now. You have a low-lying area here where more than 800 million people live. You have Himalaya, you have Central Mountain Range, so it's a low-lying valley. You are emitting pollutions, the pollution cannot disperse north or south, so it's a kind of oscillating east and west. And of course, meteorology then traps the pollution close to the surface. So you have very, very high pollution level in 1st January. And let me run this video and you see that once we move from 1st January, then comes February, you see that spatial patterns have started changing a bit. Spring comes in March, temperature increases, boundary layer expands, and you see now there is less red. But in summer, now you have dust emitted from the desert, and occasionally you have this dust sprayed across the Indo-Gangetic plain in form of dust storm. But otherwise, mostly, things are bitter. And then you see in July, when the monsoon engulfs the entire country, mostly it is blue. That means less than 40 microgram per cubic meter. Except occasionally, even in monsoon, also you have dust emitted. But otherwise, till monsoon is there, you have high pollution, and then monsoon withdraws in September, early October. You again see this pollution build up. Plus, in October, you have stubble burning and other seasonal sources. And again, the pollution sort of spreads across the Gangetic plain, and in winter, then spreads across the entire country. So, this is your seasonal cycle, very well understood. But at the same time, when you look into this kind of satellite derived product, you get much more confidence in your data product. And of course, you can see that unless you live in Himalaya, you are not really breathing clean air anywhere. We now have also data set, not just 1 kilometer by 1 kilometer for the entire country, but for a city where you have more ground stations, you can further downscale and get a very close view of the pollution. And this is the example of Delhi, where we are now mapping pollutions at municipal ward level. And even within Delhi, if you see long-term average, like this is where IIT Delhi is, where your annual concentration is somewhere around 60s and 70 microgram per cubic meter versus some part of Delhi where your annual concentration is 130 plus. So even within Delhi, you can see that people's exposure varies let's say from 70, 75 microgram per cubic meter to 130, 140. Very large variations. So the question is everyone equally exposed and equally affected? We have answered the first questions that not everyone is equally exposed. Depending on where you live in a city, where you live in the country, your periodic or episodic exposure, long-term exposure will vary. Now we'll see whether everyone is equally affected or not. For that, as I said, you need to bring health data. As I said, we exploited a lot the secondary health data like National Family Health Survey. These are the government surveys where every district of India randomly urban and rural clusters are selected. And then within each cluster, again randomly 100 to 150 households are chosen. Surveyor goes to the households, administer a questionnaire, asking a lot of questions about the women, men, about the household, children, and also collect information like blood pressure, hemoglobin level, and many other parameters, and then report it back. And these surveys are done in every few years. Most recently, the sixth round of survey is completed. The gross summary is out. Actual data will be released in a couple of months. We have exploited the last two rounds of this survey, plus there are many other surveys also very similar to this, which provide very detailed information about the health outcomes and many other variables that affect the health outcomes. Now, because you know the location of the household where the survey is conducted and health information is available, you can assign environmental exposure very precisely based on the gridded data that I explained earlier. And then you can do the analysis. And I'm showing one example. And as I said that we not only have PM 2.5 information, but we also have information about NO2, ozone, and formaldehyde. And by compiling information of PM 2.5, NO2, and ozone, we have mapped air quality index across the country. And this is, I'm just showing one example. More recently, we published this paper, 2005 to 2017, how the air quality index has changed over the years. And now we have also updated the data till 2023. And then we used health data from National Family Health Survey. And here I'm showing one example where we looked into anemia among women. Anemia is detected based on the hemoglobin measurement in the survey. What we found is that as your air quality index increases, and here we assign long-term exposures, you can see that probability of anemia prevalence after you adjust for all other risk factors. It's not a simple correlation, what I explained earlier in the first slide. You take care of all other risk factors, including diet and many other things that can also result to low hemoglobin or anemic condition. You assign how much of that risk you can attribute to air pollution only after you take care of everything else. Two important points. One is that as exposure to AQI increases, risk of anemia increases. Second information is that if you follow AQI, you know that there are certain ranges. For example, AQI more than 100 till 200 is known as moderately polluted. However, if you see that within that moderately polluted range, the outcome is not uniform. That means people who are exposed to AQI, let's say 125, versus people who are exposed to AQI 175 has a different odds of having anemia. And similarly, now we have done two other health outcomes. We are getting very similar information of nonlinear increase of the risk. Even what is dubbed as satisfactory range of AQI, we are getting some health risk. And you can also make a comparison that which pollutant is giving you higher risk in terms of PM 2.5, NO2, and ozone. And of course, what we have found is that the risk is much more for PM 2.5 compared to NO2 and ozone. So this is just one example to show that if you have this kind of information from satellite, you can actually generate evidence with Indian health data. I don't need to really model. Now, here we are talking about multiple pollutants, but within PM 2.5, as aerosol scientists, you know that PM 2.5 composition can vary. PM 2.5 can have black carbon, organics, secondary inorganics like sulfate, nitrate, ammonium, dust, and many other things. Most of the epidemiological studies so far has focused on PM as a mass. We have not really understood the role of composition or toxicity in impacting our health. Because if you talk about PM 2.5 in Rajasthan or close to desert, 50% of it is probably dust. But if you go to another place where you have a lot of coal burning, you may have very high percentage of sulfate. Or if you have large biomass burning, you may have very high fraction of organics. So we also now generated information about PM composition. And I'm just showing one example for black carbon. And you all know that black carbon is a climate forcer. It's a short-lived climate pollutant. And there is a lot of interest in understanding black carbon. So what we did is that we without going into too much details, now this paper is published in GeoHealth. So we ran chemical transport model, and from the chemical transport model, we derived the black carbon mass concentrations. Then we calculated the mass fractions of black carbon. We also considered meteorology and other predictor variables. And then we trained machine learning model to predict black carbon. And if you see that when we were training our machine learning model, the model shows very good match, but it's not an independent validation. For independent validation, we took black carbon measurements using instruments like athalometer all across the country, whatever data we could gather from literature. And you can see that predicted black carbon mass concentration versus actual measurements on ground level. Again, we achieved a very high R square value. The slope is very close to 1. Slope, there is some underestimations, but overall there is a quite reasonable prediction. And for sites where you have long-term data, you can also see that the model is able to predict the temporal pattern quite reasonably. The advantage is that you have now this sort of map for the entire country. Again, you can see that Delhi has, of course, the highest, Delhi and surrounding area. Black carbon alone, annual concentration is more than 10 microgram per cubic meter. Overall, across the Indo-Gangetic plain, the values are in the range of 6 to 12 plus. But there are other places where black carbon concentration is not that high. And now using this sort of black carbon concentrations and other species, as I said, we are doing health studies to really understand which species has more impact. And I'll show you one example later on. Coming back to air quality index, I showed one example, and based on our analysis, what we are proposing is that because the health outcome is not uniform when you are exposed to ranges of air quality index, if we are really concerned about air pollution because of the health impacts, we are now proposing that air quality index, which is only looking into the concentrations, must be updated, or you can say converted, to air quality health index, where you actually consider the city specific or region specific health data. And I will give you again example. And again, this paper is now published where we propose this methodology for two cities, Delhi and Varanasi. Now look at the current air quality index proposed by CPCB. If the air quality index is 300 plus, the air quality is deemed to be very poor. This category. Now, if you have PM 2.5 concentrations of 120, ozone 35 microgram per cubic meter, NO2 65, then your air quality index will be 300 plus. And you have very poor air quality. Now, if you do not consider health impact, both for Varanasi and Delhi, you have similar level of air quality, right? AQI is 300 plus, so it's very poor. But using actual health data from both Delhi and Varanasi, what we have calculated is that for the same level of AQI, in Delhi, there is a 2% higher risk of mortality. While in Varanasi, there is a 6% higher risk of mortality. Same AQI. Why? Because, as I said, the health outcome depends on many other factors. Many biological factors, many associated factors. So it's not same. Same AQI, two different cities, different outcomes. So now what we are proposing is that in that case, if we have to convert AQI to air quality health index, 300 AQI should be 34 to 50, what we are calling it AQHI, air quality health index. So while this will be moderate for Delhi, it will be poor for Varanasi. We must bring health actually when we talk about air quality. And now, if you have data from any other cities, any other village, any other geographical area, you can use this framework and check actually in your area what should be the air quality health index compared to the air quality index that we focus on. Using this kind of information, one can then sort of do a country level analysis and see what is happening in terms of the impact of air quality. And again, if you know, for example, in India, if you see the air pollution attributable burden, three pollutants, which is one is ambient PM 2.5, which I have been talking to so far, ambient ozone, and household PM 2.5. This is the PM 2.5 within households generated from solid fuel combustion. So the households who are still using solid fuel, they are also generating tremendous amount of pollution. And if you see from the last 20, 30 years, whatever the trends, based on the best of our knowledge, we significantly reduce the health effect of household PM 2.5 in India because more and more households are now switching to clean fuel. However, for ambient PM 2.5, actually, the burden is increasing. So the benefit that we are getting for switching to clean fuel for household activities is kind of lost due to the rising air pollution in ambient concentrations. And again, there are a lot of studies to really understand its economic impact, how to handle all of these things. Now, I must also mention that air pollution affects throughout the life. Now we have studies done in India, not only our group, but many other groups too, who have already generated information which is there in this slide. We have shown that if the mother during pregnancy is exposed to high level of air pollution, the chance of low birth weight, stillbirth or preterm birth significantly increases. If the baby survives and continues to be exposed to high level of air pollution, it can enhance the chance of infant mortality. It can enhance the chance of stunting, wasting, Undernutrition, that means there will be a negative impact on the development of the child, physical development, cognitive development. High air pollution in the childhood can increase the chance of anemia, chance of acute respiratory infections. As the child grows, there are now studies which are showing negative impact on learning outcomes. Typical school going children, I'm talking about. All these studies are existing now in the last decade or so with Indian datasets. The child grows to an adult, then there are a range of studies which are showing impact, negative impact on range of cardiovascular disease like hypertension, stroke, ischemic heart disease, respiratory disease like asthma, chronic obstructive pulmonary disease, diabetes, lung cancer, and many, many other. So overall, now we have overwhelming evidence with Indian datasets to suggest that air pollution affects throughout the life. However, if you see the age distribution of those impacts, children are most vulnerable, particularly in the first year of life, because their immunity system has not developed yet. Even if people survive in the young adult and then early adulthood, the effect is minimal because that's when you have the strongest in terms of overall immunity and all. And as a person grows older, more than 50 years, you can again see the impact of pollution significantly increases. I mentioned about particle toxicity. So this is just one example to show that we looked into a range of outcomes. The right one is for anemia, left one for three child health outcomes, as I mentioned, child anemia, acute respiratory infection, and low birth weight. Both cases, you can see that exposure to different types of PM 2.5, like elemental carbon, organic carbon, nitrate, ammonium, sulfate, you have different risks, which tells us that the risk is not uniform across the composition. In fact, we did not get any risk or any additional risk for acute respiratory infection among child if they are exposed to sulfate or dust particles. But again, maximum risk what we found is for secondary inorganics like nitrate, ammonium, and for primary species like elemental carbon. We still do not understand fully why there is this differential risk coming, what is the exact biological mechanism. But this is good evidence to suggest that we must consider toxicity. Now, people are not exposed only to air pollution. They are also exposed to many other environmental factors. So the question comes that, is there any other effect modification from other environmental factors? And if we talk about environmental factors, heat comes to mind because India is a tropical country. We have harsh summer and a significant proportion of year we have high temperature. And again, if you see the global studies, and in fact, now we have finished a study, we have not published yet, we are writing the manuscript. We also got very similar conclusions that heat actually affects the air pollution impact. But I am showing here a significant meta-analysis from 620 cities across 36 countries. India is not there. 36 countries, 620 cities, where you can see that the risk of air pollution and mortality changes as your temperature changes. And these are the percentile ranges. So what that study showed that if temperature is more than 82 or 83 percentile and above, you have the maximum impact of air quality. It clearly tells that temperature can modulate the effect of air pollution and vice versa. In fact, using our Gorvini cohort, we are also finding that heat modulates the effect of air pollution, and similarly, air pollution affects the or modulates the effect of heat on many outcomes. And we need to really understand how air pollution and heat interplay. Because, as I said, individually we are exposed simultaneously to heat and air pollution. And again, there are not many studies, evidence has started coming in, but it is an important factor to keep in mind. Last couple of slides, we are trying to reduce air pollution. We are trying to address global warming, but we all know that it will take decades before air pollution actually comes down to a safer level. For global warming, even it could take century. So is there a way to protect or minimize the effect? So we have recently started some work with St. John's and some other institutions in that directions. While recognizing that it will take time to really reduce the exposure, so is there a way to minimize the health effect? And two things have emerged from very, very initial work that we could publish. First is the green space. And second is or first here I'm showing the nutrition level. So this is one study I'm showing where we have found. So we looked into how air pollution impacts the acute respiratory infections among children. I showed some of the results earlier. Here we looked into, because in the survey we know that the children, what kind of diet they had, what kind of nutrients they are having through the diet in terms of protein, vitamins, and other things. And when we looked into very details, the dietary intake of the antioxidant nutrients. For example, if you see here, children whose diet has vitamin C more than 100 milligram per day compared to the children whose diet has vitamin C less than 100 milligram per day, what is the difference in air pollution's impact on respiratory infection? Who is more affected? Children who is consuming less vitamin C. There, 10 unit increase in air pollution, there is a 12% higher risk of respiratory infection. But if the diet is rich in vitamin C, same 10 unit increase in air pollution can only increase the risk of respiratory infection by 8%. So you can reduce the risk of respiratory infections by altering the diet. Not just vitamin C. In fact, we looked into multiple other things like vitamin D, vitamin B12, A, zinc, and many other antioxidants. And now we are expanding this analysis based on some of the cohorts that we are part of. So initially, what we are getting a sense that nutrition is very, very important. And second, as I said, green space. Again, here two examples. Anemia, because I already showed the effect of anemia. What we are finding, and we are quantifying green space using satellite derived EVI or enhanced vegetation index. And what we are finding is that if the greenness quantified by low or medium low EVI, the air pollution risk is considerably higher compared to higher EVI, indicating that people are living in conditions where the surrounding you have lot of green space. We have not looked into the pattern of green space. For example, in this study, green space is only defined based on EVI. Now we are trying to understand whether forest versus cropland versus simply grass or other types of greenness has any effect or not. But this is a good start, I will say. More research is required, but that can give us a good idea to understand what is happening. So my last slide is that we really do not know as of now how long does the pollution effect linger. For example, as I said that a mother during pregnancy, if exposed to high air pollution, there is a clear effect on the child. But is there a transgenerational effect? We do not know. There is not much evidence. For that, we need to really generate evidence at an individual level, and for that, we have to take an exposomic approach, because throughout the lifetime, an individual is exposed to many other things. Unless we really develop a capability in house to do biomarker repository and all, we cannot answer these questions as of now. Even globally, also, this question is not fully understood. How long that effect you can see? Only recently some studies have started. Probably another 5-10 years, we have some more answers on this. So key takeaways from my presentation, I think I gave small overview, but I can share more results, which talks about how air pollution has already taken a toll on the health sector in India. We have now enough evidence to act. I showed a range of outcomes for which we have now clear evidence. What we need actually is that we need to really initiate accountability studies. That means you reduce exposure, you use this sort of India specific studies, you quantify the impact, or if you reduce exposure, you quantify what is the benefit you are expected to get, and then you design your clean air action plan. So what we call this as an evidence loop. We must focus on taking this on a larger scale. And you must have understood that to do all of these things, you need different types of skill. You need modeling skill, you need data interpretation skill, you need biostatistical analysis skill. In a sense, that capacity building for interdisciplinary research is really, really critical to really take up such kind of complex interactions. You need to understand biology, you need to understand environment, you need to understand modeling and many other things. So with that, I end my presentations. I hope that I am able to give you some overview that air pollution is really, impacting us, and we need to act immediately really to minimize the impact. Thank you. And if there are any questions, I will be happy to answer.
Thank you, Professor Day. It was really a very enriching session and an eye opening one, too. So, there are several questions. I'll put some of them to you. So, one is what are the current research gaps in aerosol related health studies in India?
So if I have to summarize, of course, there is a big research gap, as I said, on the aerosol toxicity, because all the air quality guidelines or standards are based on aerosol mass. How change in size distribution and composition impacts on health, we do not have full understanding. Composition is one thing, as I mentioned, but size distribution is another thing, right? You can have different size distribution, yet same aerosol mass. So how different size distributions can lead to differential impact, we do not have full understanding. So this is one of the major knowledge gap currently, I would say. And also there is another major knowledge gap is that the synergistic effect, that how the impact of aerosols is modulated by other environmental factors. One example I have given for heat, but we have just started in that direction. So I will say there is a big gap in that direction.
So another question is which chemical species in PM 2.5 are most harmful to human lungs and health?
Yeah, I mean, so far, whatever studies are done globally as well as in India, what we are essentially getting is that, like, of course, if you have high metal concentrations, they are highly toxic. Ultrafines are highly toxic. And in terms of aerosol species, I would say elemental carbon and secondary inorganics. And not much study there in India, but based on the studies elsewhere, particularly in China, I can say that secondary organic aerosol is also very, very toxic.
So another question is how do researchers estimate long-term health impacts when satellite observations only provide snapshots in time? Okay.
Yeah, I mean, as I explained, like, long term means 10 years, 15 years, but from satellite you can generate long term concentrations, right? So far we have generated 25 years of PM 2.5 concentrations, 25 years of NO2 concentrations and all. And then you can assign exposure long term based on such information. So what we found is that 5+ years is a good example of long term exposure. So if you take 5 years of exposure versus 10 years of exposure, there is not much difference in terms of the health effect. But we have capability of generating such information now from the satellite data for at least the last 25 years.
So, another question is, how do short term spikes in ozone dominated AQI compare to PM 2.5 dominated AQI regarding daily respiratory hospital admissions?
So there are very few studies in India, but again, taking cue from global studies, yes, I think both are equally important for respiratory infections, respiratory illness related hospital visits. And the main point here is that, whether it is ozone, whether it is PM 2.5, if there is at all any spike in short term degrading air quality, there will be some impact. But I must mention one important point is that what also we know now from 20, 30 years of research is that mostly when air pollution spikes on a few days, sensitive people are mostly getting affected. Who are sensitive people? Those who have comorbidity, pregnant mothers, elderlies, newborns. People like, those who have, who are young adults and all do not have much comorbidity and not impacted by few days spike. But long-term impact is actually much more severe when it comes to the population scale.
Yeah. Sure. So, one last question, sir, we can take. How do current daily exposure models account for hyper-local microclimates without dense or localized monitoring networks?
Yeah, as I said, like, our capability, of course, we are currently doing at 1 kilometer, but if you have ground measurements, you can further come down from 1 kilometer to finer scale, provided that you have more ground measurements. Then only you can sort of train this machine learning or deep learning models. So any city where you have hyperlocal measurements or you have good number of ground measurements like Delhi, like Bangalore, like Mumbai, you can generate much finer spatial resolution. But if you do not have much ground data, so then it is very difficult to further come down from 1 kilometer.
Yeah, true. So, thank you so much, Professor Dev, for sharing your incredible insights with us today. We truly appreciate you taking the time out of your busy schedule to inspire our audience. Thank you so much for this wonderful talk today. Thank you, sir.
Sure. Thank you. I will share my PPT also. You can share with the audience.
Thank you, sir. Thank you so much.
Sure. Thank you. Bye bye.
Bye.
Okay, my slide, where is the slide?
So, welcome back. We are delighted to welcome Dr. Narendra Singh from the Aryabhatta Research Institute of Observational Sciences, AIRIS, Nainital. Dr. Singh's research focuses on atmospheric aerosols, boundary layer processes, aerosol radiation interactions, and Himalayan atmospheric environments. His contributions through observational studies have advanced our understanding of aerosol impacts on weather, climate, air quality, particularly in the sensitive Himalayan region. Sir, we are really delighted to have you here with our audience today. Over to you, sir.
My slides are visible.
Not yet, sir.
Okay.
Yes, perfect.
Yeah. Okay now.
Yes, good.
Yeah.
Good to go.
So Manu, may I know how many audience are there?
So we have around 7,000 plus registered participants, plus several of
Okay.
them are also joining through YouTube.
Okay. 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 Well. Okay. So it is 40 plus 15, right? Minutes.
Yes, correct.
Okay. So thank you very much, Manu. You have been my collaborator as well as, and we have worked together for quite for some time. And as you have given me the topic today to talk about aerosol forcing and boundary layer dynamics, so I'll be introducing first or we call basically radiative forcing or what are the fluxes that we usually measure. Then, of course, a very sort of vibrant example that we have actually observed in Himalayan region, a very severe dust storm. So I'll be talking a little bit about on this dust storm as an indicator of this aerosol forcing, that what happens exactly at the surface of the earth when we receive severe thunderstorm. Oh, sorry, a dust storm. Then, of course, atmospheric boundary layer, which is again a very, very important part of the lower atmosphere, or say the layer which is directly in contact with the Earth's surface. Then, of course, localized boundary layer also, because this boundary layer is not same everywhere. Then, of course, measurement of boundary layer. How do we make the measurements of boundary layer? And then ultimately, what is the role of boundary layer in vertical mixing, advection, all those morphological terms. And then, of course, transport of pollutants to the Himalayan region. To some extent, I'll be talking about that as well. So by now, as this program is mainly on aerosol, and so people might have been, by this time known with the term aerosols. So aerosols are basically tiny particles which are suspended in the atmosphere in form of liquids as well, and they range from 0.001 micron to 100 microns. So basically 1 nanometer to about 100 micrometers, we can say that as big as the size of a dust particle, we can say. So, and dust we all are familiar with. Everybody, I mean, we encounter every day or in daily life here and there dust, mostly, in the atmosphere or around the construction site. So the size of the dust can be as high as 100 microns. So these particles, basically what we call aerosols, are of natural and anthropogenic origin. So generally when we talk about natural, so natural things basically doesn't harm people or sort of environment much. But then definitely whenever we talk about anthropogenic things, they are definitely, some or the other way affecting our own life or our own environment. So these aerosols are of two kind. Basically, they are in terms of their physical properties, their nature of sort of interacting with radiation. Either they scatter or they absorb the incoming solar radiation. And if either of the species of aerosol absorb or scatter this incoming solar radiation directly when it is reaching to the surface of the earth or entering into the atmosphere, we call it direct effect. And when these aerosols or these particles which are in the atmosphere, they affect sort of cloud forming mechanisms or cloud microphysics in one or the other way, or they alter the sort of properties of the cloud, for example, reflectivity or their lifetime, then we call them they are. This is indirect effect basically. So direct effect is when these particles interact with the hello.
Yeah, hello, sir.
Hello.
Hello.
Actually, so sorry because whenever I'll receive call on my mobile, I'll get stuff. So I'm trying to deny all calls, but still some call is. Yeah, I have connected through my phone.
Okay.
So
Okay.
anyway, I'll reconnect. Yeah, that's the
Okay.
problem. Actually,
Okay.
I am out of office, so I'm connecting through my mobile.
Yeah.
So
Yes.
I think my screen is again. I need to reshare. I think.
Yeah.
Sorry, sorry. Uh, is
Yeah.
my
It's visible.
slide
Yeah, visible.
visible now, right? Okay,
Yeah.
okay,
Yeah.
okay. So whenever there is a call, it will be disconnected. So sorry to say that there is no
Okay.
solution to it
Yeah.
now at the moment. I do not
Yeah.
have that
Oh,
connection.
okay.
Yeah, yes. Yeah. So we were just talking about the how matter basically interacts with the radiation or particles basically interacts with the radiation, and then of course these interactions change the energy budget or energy balance uh, of the surface or surface energy balance, or we can say the other way, right? So, so the change in Earth's energy balance induced by atmospheric particulate matter is known as aerosol forcing. So, if purely because of the aerosol, then we call it aerosol forcing. But then not only aerosols are there in the atmosphere, we have many other species like these greenhouse gases, which are having even rather more impact than aerosols as far as this global warming and trapping of the radiation is concerned. So we call collectively it a radiative forcing the other way. Yes. So this is a picture basically. I mean, not a picture. I would rather say the results that we have actually or the measurements that we have actually made from Nainital. We have a CNR for this radiometer for the measurement of the radiation. So if you see that the top of the atmosphere 1368, I mean, different people quote it because these are model estimations. So they quote it from 362 to around 1370 watt per meter square. This is the radiation that we receive at the top of the atmosphere, basically the visible form or short wavelength. And when it passes through the atmosphere and reaches to the surface of the Earth, we see that the short wave downward radiation is around 450 watt or 453 watt per meter square. Under clear sky conditions. These are different conditions. So you just try to understand that how it behaves. But then what happens when radiation comes, it interacts with, it is absorbed by, various surfaces or so material on the surface of the Earth and then re-radiated back into outgoing long wave radiation, what we call generally OLR. So these radiations, if you see that under different sky conditions, so net downward and short wave upward is rather very low as compared to the incoming solar radiation. And in long wave, if you see the long wave radiation, downward long wave radiation is very, very low. And because as I mentioned that this short wave radiation is absorbed and then re-radiated into longer wavelength, so that is why it is negative. That downward minus upward is equal to, if it is plus, then means downward is higher than the outgoing long wave radiation. But in long wave radiation, it is generally OLR is higher than whatever we are getting through various interactions when it passes through the atmosphere. So this is a picture sort of actual picture of the atmosphere if you see in terms of incoming solar radiation and outgoing long wave radiations, the energy balance between, if you talk about. So that entire energy balance is basically the sum of the total incoming and outgoing radiation. Whereas a part of this radiation goes into the Earth's surface, and we call that basically in terms of, we measure it in terms of gases, and then some portion of the, if we try to balance it, then some portion of the radiation is converted into sensible heat flux. Then other part of that is basically this latent heat flux of the atmosphere, when the phase change takes place in the atmosphere, like water vapor gets converted into condensed water vapors, or sort of rain. So at that time also there's this transformation from one phase to the other, releases latent heat. So this balance basically we call atmospheric radiation balance, or say surface energy balance, or in terms of the energy balance simply if we call of the atmosphere. So these are some of the definitions that you people might have gone by this time through these terms. So radiative forcing basically quantifies the change in the Earth's energy balance, as I just mentioned, and these are caused by either natural or anthropogenic factors. So that, and ultimately these factors create changes in the climate system basically. So the change in the net radiative flux, incoming minus outgoing radiation, whether it is short wave or a long wave, we have to quantify these separately. And if we talk about this difference at the top of the atmosphere, then we call it top of the atmospheric balance. But this is happening in between, in the atmosphere. If we make the measurements in between or try to calculate in between, so we call it atmospheric warming or cooling in the, say lower troposphere or something like that, where we live. Or if we are measuring at the surface of the Earth, so we call it energy surface of the Earth. So this is relative to basically when we try to calculate it. Because the climate system is getting affected only after when we had this industrial revolution. So after the industrial era, which is, when the Western world started with measurements, with the industrializations, so it is considered after 1750. Um, this radiative forcing, which is denoted by delta F. So this is basically that perturbed term minus the reference. Reference means whatever it was at the beginning or at the end of the 1750, when these sort of calculations or estimations started. So if we subtract it from the current situation, or any with reference to that 1750, say after 100 years, 200 years, or say within a climatic epoch that we consider of 30 years. So then we can say that, okay, this is the total change in the sort of basically energy. Forcing means watt per meter square. Generally, we talk about whether it is outgoing long wave radiation or it is incoming radiation. So here you can see that this term delta F is, consisting of short wave downward short wave radiation minus minus upward short wave radiation plus downward long wave radiation minus upward long wave radiation, which is perturbed term, for example, with respect to say 1750. And then we try to subtract the reference level, which was there in 1750. So whatever value we get, we call it the radiative forcing with respect to the reference level. So this is how we calculate radiative forcing. So now how to understand it? So what could be the physical interpretation of this radiative forcing? So when we talk that if we are trying to calculate it at the top of the atmosphere, atmospheric radiative forcing at top of the atmosphere, and it is positive. So it means that more energy is getting, retained back by that Earth's atmospheric system, and it is warming. Positive means, as I mentioned, that down minus up. So if downward is uh, higher than upward, then it will be always positive. So positive means the whatever energy is coming from the sun and entering into the atmosphere, so major portion is getting absorbed or redistributed within the atmosphere itself. And if it is happening that way, so it means it will definitely try to have some impact on the atmosphere. Either it will warm or cool at some point of atmosphere. So that is why, but then since it is retained in the entire atmospheric column, so we call it warming. So if atmospheric radiative forcing at the top of the atmosphere is less than zero or negative, we can say, so it means that more solar radiation is reflected back to the space. So whatever it is coming, more is going back. So it means it is cooling the atmosphere. So basically, it is not allowing sort of radiation to penetrate deep into the atmosphere and reaching, not allowing to reach at the surface of the Earth, getting reflected back through the clouds or in the upper atmosphere itself. If this is the case, then we call that it is basically cooling the atmosphere. And then if at the surface of the Earth, if we are measuring atmospheric radiative forcing is basically less than zero or negative, it means less solar radiation reaches the surface of the Earth, and it is called, it will definitely reduce the temperature of the surface of the Earth by say of less than a degree or so. Then we'll say that it is surface dimming. And if it is positive at this in the atmosphere, within the atmosphere, not at the surface, say I say around 4 to 6 kilometers, say a column of 4 kilometers or 6 kilometers, where we consider that aerosols or water vapor cannot go higher up beyond that say 6 kilometers. So in that case, these aerosols which are present within this 6 kilometers of the atmosphere, they absorb radiation within the atmosphere, and they will, if this forcing is positive, it means they will heat the atmosphere. So that is how we calculate the atmospheric heating rate in the troposphere. Say, for example, we have measurements of all these fluxes at say 100 meter, 200 meter, and so on, or say 1 kilometer, 2 kilometer, or somehow using lidar data. Sometimes we calculate all these things. So there we can calculate that what is the basically atmospheric heating rates at within this kilometer, something like that we can calculate. So these are sort of uh, top of the atmospheric forcing highlights. If we talk about it, that it indicates that net impact of the aerosol on the Earth's planetary energy budget. And surface forcing basically represent the reduction or enhancement of radiation reaching the Earth's surface. And as I mentioned that it measures the radiative heating of the atmosphere due to absorbing aerosols, if we called atmospheric forcing only. And like, for example, black carbons, if you people are aware about it, nowadays we are trying to understand that due to the forest fires in the Himalayan region or say fertile regions or say crop residue burning, a lot of black carbon is produced. And sometimes these black carbon particles, or say this black carbon nanometer particles, are going up to higher up to the higher reaches of the Himalayan, and these are basically absorbing type. And once they reach to the glaciers, or even dust is also absorbing type, it settles over the glaciers, so they absorb more radiation and try to reduce the the snow cover or snow cover depth there itself. So these are having negative impact on. So this can be one of the negative impacts of these uh, uh, black carbon or aerosols, you can say. So this is generally, I mean, the IPCCU people are aware about Intergovernmental Panel for Climate Change. So they carry out study over, say, 5 years or 10 years. They every 5 years or in that span, they produce their reports, and they try to assemble the global data and various models, observations, and then try to predict, based on the available information, that what is going to happen by the end of this century. For example, if we talk there about the global rise in the temperature, so by the end of this century, most of the globe is going to warm, but then North Pole, South Pole, and Himalayan region are the most or the badly affected regions. Basically, Himalaya is going to witness the rise in the temperature as high as 5 to 7 degrees Celsius by the end of this century. So these are sort of studies which are carried out by the IPCC. So now, as I mentioned, that it impacts the surface layer characteristics. Surface layer characteristics basically are the various fluxes which are part of the surface energy balance, and then of course columnar change in the temperature also, top of the atmosphere also. These estimates are also there, but then if you see that we made a measurement of a dust storm. We have some ground-based instruments at our site in the Himalayan region. And if you see that generally in normal conditions, we have most of the time, these are PM 2.5. Particulate matter is also a kind of aerosol, which is having aerodynamic size less than 2.5 micron and very, detrimental to the environment and health, human health. So these PM 2.5 measurements are getting very important nowadays to be measured. So generally what happens, these are whenever we have normal measurements over a given day, mostly we are having 20 to 25 microgram per meter cube, the whole day. I mean, any at any point of the day, maybe within 5 to 10, plus minus 5 or 5 to 7 microgram per meter cube variations. But whenever there is a severe dust storm, which is originating far away in the desert of the African region, Sahara Desert or northern part of the African region, and then passes through the Arabian deserts. So these deserts basically supply a lot of dust with the storms, and we call it dust storm. So this was a dust storm which was observed in uh, June 2018, around 8 to 22, this period in between. So what happened? All of a sudden, you can see that this PM 2.5 has, reached up to 300, 250 to 300 microgram per meter cube. So, and these are the AOD. This blue curve is basically aerosol optical depth, estimated from Moody's data. So, whenever there is a storm, AOD also goes beyond 2 to, 2 to 2.5 or 2.5 to 3. It reaches to that level. So it means the dust has approached to this region. So along with the dust, not only dust comes, but polluted dust when it passes through urbanized regions. So it becomes dust when pollutants also stick over the dust, other pollutants, and it becomes polluted dust. So in that case, if you see here, that we then tried to estimate that what was the amount of dust that had entered from the western part of the world, or basically from the desert part of African or this uh, Arabian region. But then when it passes through the western part of our country, like Thar Desert or this Rajasthan region, then approaches to Himalayan region. So what happened in that process? If we see the contribution of our own, deserts, it is around 2.5 teragram. So 2.53 teragram, we estimated that it came along with the long range transport, which with the dust storm, which originated very far away, very far off in the African desert. And then, of course, the contribution from Indian region is also even slightly higher than more than 50% contribution is from our own region. So, and it, adds to around 4.8 teragram dust in the atmosphere. But when it reaches to the Himalayan region, if you see, what are the impact? So these are basically surface characteristics. We try to make the measurements of all three components of the wind using a sonic anemometer at 10-meter altitude, put on a micrometeorological tower. So here you can see that during dust storm occurred actually during 13 to 17 June. 8 to 12 June, 5 days we have taken, just 5 days before the dust storm, and then 5 days after the dust storm, what are the changes? And then these 5 days when dust persisted in the atmosphere, you can say. So, of course, whenever there is a storm, winds also go very high, reaching as high as 6 meter per second, zonal component basically. And of course, this vertical component is also very high. You can see that around 4 meter per second in case of meridional component, sorry. And vertical component of the wind is also slightly higher, reaching as 40 centimeter per second. So it's relatively higher as compared to the normal day. Generally, we have 10 to 12 centimeter per second on a given day. So then, of course, mostly since the west, so you can see the directions are close to the westerlies or northwesterlies. So here, if you see, then the temperature before, during, and after. So the temperature, this red is basically just before, the dust storm, and then black is during the dust storm. So during the storm, you can see that temperature has dropped by say around it is if you take 21 degree on an average, and it has gone to in the daytime, the maximum temperature if you talk, it has 21. So 3 degree, there is a almost 3 degree change in the temperature. So that is what I mean. If you aerosol forcing, if you can see that these dust particles are basically absorbing type aerosols in the atmosphere, and they absorb the radiation. Doesn't they scatter less but absorb more, and do not allow the radiation reach to the surface of the earth. So therefore the temperature drops. So here you can see that sensible heat flux, which directly translate into the what we call the hotness and the coldness of the system. So here also you can see that the sensible heat flux has gone down because the temperatures are not coming. I mean, the radiation is not reaching to the extent it used to be on the surface of the earth during a dust storm. And then turbulence is also there because U, V, and W, all three components of the winds are perturbed. So this turbulent kinetic energy, if you see, this is also, very high in that case, reaching up to as high as I mean, deviation in terms of 40 meters square per second square, if you talk about. So this is how we can see the impact of a dust storm on our surface layer characteristics or surface parameters like sensible heat flux or the temperature. Temperature has dropped by 3 degrees Celsius during a dust storm in the Himalayan region, and immediately after the dust settles, temperature again 18 to 20 June has gone up to 24 degree Celsius. So these are some of the calculations done by basically again on radiative forcing by IPCC, if you say with respect to the 1750 watt per meter square. So total anthropogenic radiative forcing, if you see relative to 1750. So by 2011, it is 2.29. You can see here, the change in the sort of, if we translate into the temperature. Then there are other, culprits also, not only this sort of aerosols, but then there are other gases, greenhouse gases, and short-lived, long-lived, all greenhouse gases are there. I mean, species in the atmosphere, gases and aerosols. So this is sort of a picture where you can see that mostly the contribution is coming from, of course, CO2 is one component, but then mostly man-made activities. And this is again this I mean sort of similar picture, but then the point is that do we need to worry about this sorry radiative forcing? So 17 by this is the simulated temperature contribution in 2019 relative to 1750. And the previous one was basically, if you see, three climatic epoch, 1950 to 1980. One climatic epoch is considered to be 30 years. And then 82 to 2010, you can say every 30 years or 11, because IPCC report came in 2011. So forcing has doubled in every climatic epoch, roughly. I mean, it was around 60 if you consider. So it has become 120, and then 125 to around almost 230 it has gone. So close to double, you can say. So every 30 years, the radiative forcing or anthropogenic radiative forcing is getting doubled. So this is a very alarming situation in a way, you can say. So now this was briefly about the aerosol forcing or how aerosols control the atmospheric sort of radiation budget and cloud microphysics, everything they impact. But then how do these go higher up into the atmosphere? So this is again a very, very important point. So now coming to the boundary layer, generally, what is the boundary layer? So, boundary layer, those who are from atmospheric science background or those who have gone through meteorological some courses, they might have heard about the Stull, Ronald Wistall's work on boundary layer and meteorology. So, he has written a very nice book on boundary layer. So, most of the content I know what we use for teaching is from there only. So boundary layer is basically, if you see, I mean, generally, how do we realize that what is boundary layer? Because it is invisible in generally when we talk about the atmosphere. Atmosphere is almost invisible to all of us. So when you take off or land in the airplane, then you see that there are some bumps or, your aeroplane, you feel sometimes shaky or something like that. So these are basically, or whenever, I mean, it's landing, mostly it goes up and then comes down. So these bumpy layer near the ground is basically planetary boundary layer. I mean, you can say that this is the influence of that boundary layer, right? So the boundary layer is basically the lowest part of the atmosphere, which is directly influenced by the presence of the Earth's surface. And it responds to the surface forcing. Forcing, you have, by this time, you are familiar with the forcing is basically nothing but the response of the atmospheric composition or atmosphere, atmospheric air to the solar radiation. Simply you can say, if we talk about the surface means earth surface, and forcing means which is exerted by the surface of the earth in response to solar radiation, simply either by heating or cooling. So but the boundary layer evolution is a process which takes place only in the presence of sun. Of course, there are some other mountain meteorology. Some this is different. I'll be slightly later. I'll be telling you, trying to explain that also. But then, generally, when we talk about the boundary layer, it is basically the lowermost part of the atmosphere, and which responds directly to the surface forcing. And say it takes about an hour or less, around 1 hour. When in the morning, if you see that sun rises, so after 1 hour, you'll start seeing that mixing in the atmosphere. So it is known as atmospheric boundary layer, or sometimes it is defined as planetary boundary layer. So atmospheric boundary layer or planetary boundary layer, when we talk about, so planetary boundary layer or atmospheric boundary layer are same. So same in the sense that whenever we talk about planetary boundary layer, it is basically across the flat terrain. Generally, we talk about all across the globe. The boundary layer over the flat terrain is generally atmospheric boundary layer or planetary boundary layer. For example, uh, if we try to make the measurement globally from starting from equator to mid latitude and then going to the poles, so and then try to take an average boundary layer, that what would be the mixing depth or sort of boundary layer in the atmosphere. So it is somewhere between 1.5 kilometer or around that, less than 1.5 kilometer. But then what would be about the place which is already 1.5 kilometer above mean sea level? So that is why we talk about the
Dr. Narendra, you're not audible. Ji?
is it visible again? I've got a call
No, that's
again.
yeah. Yeah, now fine.
visible, right? So it gets disconnected and then reconnect. By the time I, got
No
the call.
problem. Okay, okay, no problem.
Yeah. So, yeah, so this planetary boundary layer and atmospheric boundary layer, as mentioned, is the same. And sometimes people call it convective boundary layer. There are a number of terms for this. Different books or content will use different terms. So convective boundary layer is also same, but this is convective is generally daytime boundary layer, because wherever there is sun, so it will heat up the air, thermals will rise up, and a mixing will take place to some extent. I mean, as long as the surface forcing dominates. And then free troposphere. So the boundary or the highest level that this mixing due to the response to the solar radiation can achieve is basically sort of the mixing depth or the planetary boundary layer or the convective boundary layer or atmospheric boundary layer. But beyond that, the region of the atmosphere is called basically free troposphere, because this is a tropospheric phenomenon. Everything happens in the troposphere. So troposphere gets divided into two parts. One is planetary boundary layer, or other the part above that is basically free troposphere. So generally, I mean, when you read papers, you will see that many places it is written free troposphere. Then again, it becomes sort of confusion, state of confusion for the students or the people, that what is then free troposphere. So this is the term, that's why I've written here. So free troposphere is just above the boundary layer, and boundary layer may vary from one place to the other, from one region to the other, and from one season to the other. Planetary boundary layer is not same what we observe in May, June, or it will not be same as in winter, because you see a lot of fog formation in the winter, say within half a kilometer, whereas in summer you don't see that. So these are basically the influence of the evolution of the boundary layer. So now, yeah. Yes. So this is, you can see that this is a schematic. The first picture of Stull's book. I mean, this is what people use for basically boundary layer representation. So this is above the region above the boundary layer. This is its Earth surface. Then the extent of mixing in the daytime, and this is the troposphere if you talk about. So these are, I mean, since we are in the tropics, but troposphere is not at 11 kilometer, neither boundary layer is at 1 kilometer. But then these are the books written by the mid-latitude people. So there, of course, this is true for mid-latitude. So this region is pre-troposphere, where beyond that, just above the boundary layer is pre-troposphere. So now, how do these processes happen in the atmosphere? So in the transport process in the atmosphere, in the terms of the wind and flow, it takes basically in the following way that the lowest 100 meter to 3000 meter of the atmosphere is basically generally modified by the surface forcing, right? So over desert, if you try to make the measurements in the summer, maybe the boundary layer there will be 3000 meters, which is not possible at flat land or ocean or anywhere else. So turbulence is one of the important transport process. How do the momentum, energy, mass, or everything, whatever you water vapor or say aerosols is taken higher up in the vertical, is because of the turbulence. If there is no mixing, turbulence leads to mixing basically. And what is turbulence? Basically, these are turbulence is basically the gustiness simply superimposed on the winds, basically, you can say. And then, that takes, that is sometimes thermally driven, sometimes it is mechanically driven because of the wind shear or directional change in the wind, or say magnitude change in the wind. So these are the sources of the turbulence in the atmosphere. So, and then this airflow, of course, which is basically part of the global circulation, sometimes very localized circulation. So this is divided broadly into three categories. One is mean wind. Mean wind means if you try to make the measurement of the wind the whole day, and you find that, okay, wind is fluctuating between 1 meter to 1.1 or 1.3, something like that. So the whole day, sometimes it becomes 1.3 meter per second, another time it becomes 0.7. So, I mean, so it is oscillating between these 2 points. So we can say that the mean wind is around 1 meter per second. And of course, as I mentioned, that turbulence, of course, suddenly wind is increasing, or it is wind direction is changing. So it will be thermal or, mechanically driven turbulence. But because of the radiation, if it is, W component is sometime increasing, trying to subside the horizontal component. So there will also be changes in the turbulence in the winds. And then third one is basically waves. Waves are basically regular patterns in the atmosphere, periodic patterns in the atmospheric winds, and we call them waves basically. So these are sort of the processes that operate most of the time in the atmosphere, and these can coexist sometimes in the presence of one or the other, and these quantities are responsible for to take up in the moisture, heat, momentum, and pollutants in the vertical.
We are waiting Dr. Naren to join back. Some network issue at his end. Please wait for some time.
Hello.
Yes, yes. Now you're audible,
Ah,
sir.
Manu,
Yeah.
okay. So, as I just mentioned, that boundary layer is basically a process, the portion of the atmosphere which, is responsible for all sort of mixing in the atmosphere, right? So, if we try to make the measurements over ocean, so in the oceans, you will see the boundary layer relatively very slow in the space and time. You will see a very sort of flat and uniform structure. You will not see many spikes and up and down during the mostly whole of the day. Even in the daytime, there will be slightly a few hundred meters or less than, I mean, not few hundred, 100 to 200 meters changes in the daytime, but not like half a kilometer or something like that mixing. So because the heat capacity of the water is very high, so it slowly absorbs all heat and warms slowly. It doesn't warm faster like land. So that is why we have land breeze and sea breezes in the daytime and nighttime. So over both land and ocean, the general of the boundary layer is to be thinner in the high pressure regions and low pressure, thinner than the low pressure region. So basically, if you have a high pressure region means there definitely the mixing will be slightly slower in the atmosphere, and low pressure region it will be already turbulent, and of course the higher temperature at the surface, so the boundary layer will be higher where the surface temperatures are higher, or of course surface it is a low pressure region. So over land surfaces in the high pressure region, the planetary boundary layer has a well-defined structure and evolves with the diurnal cycle. The three major components of this structure are, so in the daytime, basically it's talking about the daytime boundary layer evolution. So there are three components of this structure. If we take, say, not daytime, if we talk about the diurnal cycle, means 24-hour cycle, starting from midnight to another midnight. So if you see that, then there are three components. One is mixed layer, which is basically in the presence of the sun when mixing takes place, and thermals form, the earth surface heats up, thermals form, then eddies forms. It takes all sort of material from the surface of the earth higher up in the atmosphere, and to the maximum height that it can achieve as a result of this surface heating or surface forcing, that is called your mixed layer. Height achieved at that moment, we can call it the mixing height or mixing depth or the boundary layer height. Then in the afternoon, what would happen at the sunset? I think from this picture, yeah, this is okay. I mean, I'll explain in the another slide. So mixing, there are three parts of the boundary layer. One is mixing layer, another is residual layer, and then stable boundary layer. So in the picture, it will be clear to you. So here you can see that wherever there is a high pressure region means mostly there will be air will be mostly suppressed, you can see. So subsidence will be there, mostly downward motions will be there. And wherever there is a low pressure region, mostly updrafts or mixing will be there. Like for example, the formation of the thunderstorm takes place only in the low pressure system when your pressure falls suddenly. So these developments take place. So this is basically schematic of ideal planetary boundary layer. How can we understand it? So this is basically sunrise to sunset. Sunrise, this yellow you can see. It starts if we
Not audible, Narenji. Again, not audible. Can you hear me?
yes,
Dr.
Manu, I think it again Windows पे चला गया.
Okay, now fine.
Is it okay now?
Yes, yes.
Yes, yes. Uh, oh. So it will. Okay, so I was just trying to explain this boundary layer picture actually. So at the sunrise, when sun comes in and it starts heating up the Earth surface. So thermals start forming, air parcels. You can see that air starts rising up and then mixing takes place. So this process goes on up to in the afternoon, you can say up to 2 or 2 3 it goes on. It starts saturating after the noon and it remains there almost stable layer. After that, when it reaches the equilibrium situation in the daytime, so it is like this. This yellow is the completely evolved boundary layer. But then, as I mentioned, that from one place to the other it varies. It will be around 1.5 kilometer over tropical region. If you go to the mid latitude region, it will be less than a kilometer. And then if you go to the poles, it will be a few hundred meters, say less than half a kilometer. So something like that. It varies from tropics to big, depending upon the amount of the radiation a place receives. Right. So then in the afternoon, after the sun, I mean, just two or around 2 hours before the sunset, when sun starts going down to the horizon, you can see then these thermals basically ceases to form. No thermals form anymore. Thermals means the warm eddies of air, you can see. And then it starts the matter which is there in the atmosphere, it starts settling down slowly. So by the time, sun sets completely, all the mass starts settling down. In the evening also, sometimes you see in the winter, the daytime, the water vapor goes up, and then in the evening, again, it settles on the surface of the earth, and you can see in the form of the dew on the surface. So that is how we can understand the boundary layer processes, that why it is happening. So this portion which is which was completely mixed in the daytime, this residual layer you can see. So this is part of the mixed layer, but then in the daytime we had a lot of water vapor here, a lot of a good amount of this aerosols and everything else, whatever in the atmospheric gases, everything goes up. So and in the evening it starts settling down. So but a portion, it doesn't completely become so clean, like still atmospheric composition is there. Some sort of lighter aerosols are there in the atmosphere, but the heavier particles come down, and then it remains something like this. This region is called residual layer. This is part of the mist in the daytime, but nighttime it again gets divided in two parts. One remains there in the form of the residue in the atmosphere. We call it residual layer, and one becomes very stable in the nighttime. Mostly everything, all mass matter settles down in the lowermost part of the atmosphere, and we call it stable boundary layer. I mean, there is no mixing or settlement in the night beyond this limit. So, so few hundred meter, you can say that 300 or 400 meters like that. But then there is another layer, you can see here a surface layer. So this is basically 10% of this part, total of the, say for example, in the daytime, the boundary layer has reached to 1.5 kilometers. So this 150 meter in the lowermost region is basically surface layer, and everything, most of the activities, all sort of your transfer of the energy to the molecular level happens in this surface layer, which is very close to this, which is directly in the contact of the Earth's surface. So this is how boundary layer evolves, starting from sunrise to the sunset, and then after sunset, a portion remains there aloft in the atmosphere, and a portion becomes stable or very much sort of well mixed, or sort of you can say that I mean, no further changes are allowed in the night. We call that stable boundary layer. And beyond that, as you know, it is a free troposphere. So these things which I have just mentioned, that these are if I mean, there are various classifications again of the boundary layer. If there are cloud, we call it cloud layer or subcloud layer. Where clouds are present, that is cloud layer, and beyond that, subcloud layer. So bottom 10%, as I mentioned you, that this is called surface layer, irrespective of it is part of the mist layer in the day, in the nighttime. And then interfacial layer, what I mentioned, that very few lowest part of few centimeter of the air, which is where molecular transport dominates. Basically, energy transport to the surface of the Earth through the molecular exchange of the energy between the Earth's surface and the molecules. Then the turbulence in the mixed layer is generally convectively driven in the daytime, because convection is the source of mixing in the daytime, not the other like strong winds or something like that. Then residual layer. These are the some salient features of the residual layer. As I just mentioned that this is I mean when the thermals cease to form and turbulence also decays, then this well mixed layer gets converted into residual layer in the night time or after the evening hours. So again, this is the same thing which I've just mentioned. And then residual layer does not have direct contact with the ground. In the ground, with the ground, only stable boundary layer has the contact. This is what these are some of the salient features of the stable boundary layer. That as the night progresses, the bottom portion of the residual layer is transformed by the contact with the ground into the stable boundary layer, or we sometimes call it nocturnal boundary layer. So daytime mixed layer is different from the nocturnal boundary layer. But then, like if you talk about the mountains, in the mountains, when in the seasonal transition of the winds, we have very strong winds of say around 20 meter up to 20 meter per second, sometimes 15 to 20 meter per second. So that time in the night also, if you see, I'll show some of the results which are take, derived from direct measurements of the boundary layer wind profilers. In the night time, strong winds are there. Time also we see well mixed localized boundary layer. So these are some different features of mountains, you can say. So although the wind at the ground level frequently becomes lighter or calm at the night, but the higher up in the nighttime winds accelerate basically, and sometimes they take the form of the jet in the nighttime. So nighttime surface may be calm, but the higher up in the atmosphere or boundary layer there are nocturnal jets. Jets means when the wind speed goes around 12 to 15 meter per second in the night, you can say. uh, so then pollutants emitted into the stable layer disperse relatively little in the vertical in the night time. So that is why, these are the features of the stable boundary layer in the winter, basically, when solar radiation cannot penetrate to the surface of the earth. So this stable boundary layer forms there, and mostly it remains for days together, in the winter time, night and day mostly same. Only say few 100 meter or so, 200 meter, it evolves in the daytime, not more than that, and all pollutants remains there in the atmosphere in the lowermost part, and it forms a layer of smog, or generally we call it fog, but that is smog basically, because these are the pollutants mostly which are forming a sort of very thin layer of the fog kind of situation. So you can say that at 200 meter above the ground, the speed may reach 10 to 30 meters. So we call them nocturnal jets. So now how to make the measurement or of the boundary layer? When we didn't have any instrument like Doppler radars, or even nowadays lead Doppler lidars are being used for the measurement of the boundary layers sometimes. Of course, these ceilometers also they are having algorithm to make the measurement of the boundary layer. But then in the absence of all these state-of-art technology, we had balloons only, and we used to launch balloon in the atmosphere, but that will also give one snapshot within say 2-3 minutes. It will cross because it is having a 5 meter per second ascent rate. So you can say that in 1 meter in 60 seconds it will cross around 300 meters. So you can say, so within say 1 to 2 minutes it will cross the boundary layer, but then it will give us a temperature profile. From that temperature profile we calculate potential temperature, and taking into account the moisture component, and also we calculate virtual potential temperature. So virtual potential temperature in the atmosphere will show a gradient, sharp gradient. So that sharp gradient indicates that, beyond that, the mass which has gone from surface to the higher up in the atmosphere will not be able to penetrate higher up, or the turbulence ceases basically at this point. So we can call this is the boundary layer. So this is how we used to make the measurement of the boundary layer. boundary layer. But nowadays, with the advent of the radar, you can see these were the first sort of lower atmospheric wind profilers which were installed by ISRO in atmospheric research laboratories like National MST Radar Facility. It used to be earlier a National MST Radar Facility. So there you can see that from one season to the other, you see the boundary layer variation. I mean, in terms of the turbulence, because turbulent kinetic, and this is turbulent kinetic energy, and this is the parameter, one of the parameters to characterize the boundary layer. So in summer, you can say that around midday, or say in the up to 2 to 3 p.m. in the afternoon, you can say the evolution of the boundary layer is highest. Here you can see, and mixing, I mean, the strength, higher turbulence means higher the strength of the mixing in the atmosphere. So it is reaching HIS 1.5 kilometer, you can see, in the vertical in summer season. Monsoon again is characterized by turbulence because we have mostly wind convection as well as the you can mechanically driven turbulence in the atmosphere, strong winds, then clouds, all these. So here you can see most of the time monsoon season is more turbulent, and boundary layer is as high as, I mean, around 1.5 or 1.6 meter, 6 kilometer in the vertical. So 1.6. So then again in winter, post monsoon, you can see that in the morning, after 9 or 10, you can see the slight evolution of the boundary layer, you can see, and it is less than, say, 1.2 kilometer, or say around 1 kilometer. And then winter is again in the afternoon, of course, here you can see slightly higher mixing, around 1.2 to 1.5, but then for a shorter period of time, not for a longer period of time, because the solar radiation is, the length of the day is, you can say, is slightly shorter than what we have in the summer. So now, this was basically, we can say that this is the representation of the planetary boundary layer generally. Of course, that is also a slightly a valley, or surrounded by mountains, very low altitude mountains. The site is surrounded NARL. But then if we talk about, I mean, such observations, so these representations are basically from the, flat terrain, or we can call it this the representation of planetary boundary layer during different season. But when we talk about mountains, so here, you can see that completely different picture with the similar measurements, similar instruments, which were basically, these observations were conducted in collaboration with the United States. We had a project. So these are very state-of-art instruments. We had an opportunity to sort of make the measurements at the top of the mountain. So now here, as if you have some feel of boundary layer, so here you can, you cannot distinguish that where is the boundary layer. This is a general picture, if you see, and this is in UTC. So you can say that this is our morning time starting around this region. So 10:30 or so, starting from 8, so something like so. This is our morning to afternoon time, you can say. And you say there is a evolution of the boundary layer, but then a lot of spikes, because mountain modulate winds according to the shape and size of the mountain, then the height of the mountain. So it is very difficult that to tell which is the boundary layer. So we call it a localized boundary layer, which basically changes from one season to again the other season. So now this is for winter. This is a case of winter measurements. So in winter, you see, uh, in contrast to the plains site, or say these NRL observations, you see that our boundary layer is evolving not even half a kilometer in the vertical. You can see here, right? So starting from this here, and then from midnight to in the afternoon, if you see here. So this is around sometime. I mean, if you take that, okay, some sort of mixing, this lighter mixing has taken place up to around 600 meter, but still the dominant mixing is around 400 meter or so on a given day. So these are sort of observations over the mountain. So mountain sites are very behaving very differently, and we call it localized boundary layer, not exactly the planetary boundary layer or sort of the convective boundary layer kind of things. So in reference of the atmospheric boundary layer, we cannot say. So again, in spring season, or say just before pre-monsoon season. You see, in the March, we are having strong winds at Nainital, if you see. So, as I mentioned, that sometimes we receive 20 meter per second or so, 15 to 20 meter per second's wind. So, very, very high wind. So, in the morning or afternoon hours also, you see here the mixing is around 700 meter or 800 meter. But then in the night time also, you can see that there is mixing. Whereas in the nighttime, in the absence of the solar radiation, if you see, there should not have been any mixing in the vertical. So it means the horizontal winds which are directly striking to the mountains, they are getting, sort of breaking into the various flows and then creating turbulence in the atmosphere, which is responsible for again for the mixing in the nighttime as well. So these are the differences that we clearly we can see in the sort of measurements over a mountain side, which is complex terrain, what we call everywhere, whether it's Himalayan region, Alps, or any other regions you see. So we'll mostly see similar sort of observations depending upon the height and the complexity of the terrain, mountain. So these are, I mean, some very simple things that really talk about that. What is the significance of the boundary layer? That the first significance is it is responsible for the mixing of everything higher up in the atmosphere. I mean, taking from the surface to the in the vertical. And we spend most of our life in the planetary boundary layer, and all these forecasts that we issue for every day for our informations, whether it is dew, frost, maximum, minimum temperature, or whatever. These are basically boundary layer for forecast or boundary layer features, you can say. And pollution is also trapped in the boundary layer, which sometimes results into the fog, particularly in the winter. Then aviation, shipping activities, everything is conducted in this portion of the atmosphere only. And primary energy source for the whole atmosphere is solar radiation, and which for the most part is absorbed at the ground. I mean, whatever as I mentioned, that short wave radiation is reaching to the surface of the earth, it is absorbed by the earth's surface and then re-radiated back into outgoing long wave radiation, which is basically responsible for the heating of the atmosphere. So this is how, boundary layer, and then boundary layer responds to these heating. And so this is what it exactly mean. Then crops are grown in the boundary layer, all activities basically what we can think of. Cloud nuclei are stirred into the air from the surface by boundary layer processes, because cloud formation will take place only if there are cloud nuclei or cloud condensation nuclei which are taken up higher up into the atmosphere, and they sort of they are hygroscopic in the nature. They attract the moisture, and then ultimately condensation takes place and clouds form, and then ultimately results into the rain. So all water vapor that reaches in the free troposphere is the first transported through a boundary layer turbulence or the advective processes. Advective means we do not have, basically every place is not having moisture. So where does the moisture comes from in the atmosphere? It is coming from the oceanic regions, which are very far away from the continental part. So how does it come? It comes through the advection. We call the horizontal transport of the matter, energy, mass, water vapor is basically advection. So with the horizontal flow, whatever comes into the atmosphere is called advection. So then thunderstorm, hurricanes, all these are, tied to the inflow of the moist boundary layer air, So they take all moist air higher up in the atmosphere and result in the atmospheric phenomenon like thunderstorms or hurricanes. So 50% of the atmospheric kinetic energy is dissipated in the boundary layer. So that is why boundary layer is, estimated in terms of turbulence, or say energy dissipation rates, or we can say, and even turbulent kinetic energy at the top of the boundary layer also can be calculated. So this is basically all from my side. So I would be happy to answer if you people are having questions. Thank you, and I'm really sorry for the interruption in between.
Thank you, Dr. Narendra. It was such an informative and enriching session. We have several questions, but I think we can take a couple of them. We are approaching towards the closure of day one. So one is, how do temperature inversions affect the boundary layer and pollutant dispersion?
See, inversion is a basically portion of the atmosphere, where the temperatures become slightly stable. Because in the troposphere, when we talk about the temperature decreases vertically as we go higher up in the atmosphere at the rate of 6.5 degrees Celsius. So basically, whatever energy, mass, momentum, or turbulence which is created in the atmosphere, it ceases at that region where we encounter these inversions. Basically, inversion is basically slightly stable layer in the atmosphere where all our surface forcing can't penetrate, and we call it the top of the boundary layer. So these are basically responsible in a way to put a sort of lid on the portion of the boundary layer in the atmosphere, and beyond that these pollutants cannot penetrate all of a sudden unless strong forcing is there in the atmosphere. Yes.
Yeah. Mhm. Another question is, in what ways does the long wave radiative cooling of a humid aerosol laden residual layer trigger early morning elevated fog formation over regional plains?
Yes, this is, we have to understand basically two processes. How does this, I mean, the early morning formation of this fog sort of things are concerned. These are basically phenomena generally which are taking place as relatively pristine site. If your lot of sort of these pollutants are there, so mostly moisture gets distributed. So you will not have a very much pure sort of these formation of these sort of layers or the situation which this question is concerned with. So it is basically depending upon the cleaner side when we have lot of cesiums which are able to sort of acquire that moisture, and they slightly rise up early in the morning just before the sunset or just around the sunset, and then all of a sudden they form this hazy situation. But that is not sort of related to the pollutant, because if in this COVID for time in Delhi also we used to have this situation. So the mechanism operating at that time is totally different. But then whenever there are induced pollution, anthropogenic pollutants there in the atmosphere, so this situation will not be that common, but only in very low temperature conditions they will form. But then that will be sort of smoke kind of situation. So these two situations are totally different. Yeah, one
So one
forms in
last
pure.
question. Yeah.
Yeah.
Yeah. True. So, last question we can have, can satellite data accurately capture aerosol planetary boundary layer interactions?
Not really, because satellite resolutions is so poor that if you have to, monitor at least from sunset to sunrise, the sort of our atmosphere. So what would happen that we require sort of continuous, at least half an hour measurement, at least we will require to have that information of mixing in the vertical in any form, whether it is sort of AOD or, I mean, of course, from AOD we cannot directly do that. But then, like Calypso used to be a lidar, which is
Again, network issue. Yeah, I think most of the question has been answered by Dr. Singh. So, on behalf of the entire IIRS team, I thank you, Dr. Narenji, and we especially appreciate you joining us remotely and presenting despite not being in the office today. Your breakdown of boundary layer dynamics and aerosol interactions made a complex topic incredibly clear and engaging for everyone. Dr. Singh, thank you again for your time, effort, and taking up all our questions. Thank you so much.
Sorry, Manu. I was really so, disturbed by these calls today or interruption.